So let's start. Next plenary talk will be given by Manfred Husty. The topic is from mechanism to kinematic constraint equation. Manfred is from Austria, from the University of Innsbruck. He has master degrees, PhD degrees about the field theory in non-Euclidean spaces. He has also an honoris causa degree from Technical University of Cluj-Napoca. He's full professor of geometry at the University of Innsbruck. He was the dean of the Faculty of Civil Engineering. His main interests are computational kinematic, classical geometry, no-Euclidean geometry, and differential geometry. He was a member of the Center of the Intelligent Machine at McGill University in Montreal, Canada. He grew services as chair of IFToMM Austria, and he was a conference chair of Advanced Robot Kinematics, LCOMES, and Conference of Geometry. Met Rob, he was his journal editor of Journal of Geometry and the Canadian Transaction, Canadian Society of Mechanical Engineers. He won several awards, many best paper awards on IEEE, LCOMES conference. He has the most cited mechanism machine theory paper about the finding the solution of the Stewart platform. He has also awards in geometry, more than 50 indexed journal publication, 50 chapter in book, 50 conference, 6 books, and many more production. Please welcome to Manfred Husty. We are very honored with this talk. Thank you, Manfred, for accepting to give us your lecture. Thank you very much.
Yes, I'm trying to share my screen. I hope that will work.
Yes.
And as I can see, I hope you can see my screen. Thank you very much, Martin, for introducing me. It was almost too much, but I'm happy that I'm allowed to give you a talk on the topic of mechanisms. And what I will talk is essentially about mechanisms, and from mechanisms to the mathematical representation of mechanisms and what you can do with the mathematical representation. The overview of my talk is, after a short introduction, I will briefly talk about the mathematical framework we are using. The most important ingredient will be the notion of constraint manifold, and from constraint manifold to constraint equations. I will run through the possibilities of this mathematical framework by showing you how it works on a simple planar 3-RRR parallel manipulator as a paradigmatic case. And depending on the time I have, I will show you different other examples. So the 3-RRR manipulator is just a simple case to show you how the framework works. I am myself working within a branch that is called computational kinematics. Martin has told you that I was chairing within IFToMM, the computational kinematics group, for several years. And the statement of Jorge Angeles is from the year 1993, but it's still valid, and it has become even more important because the capability of the computer systems doing symbolic computation has increased within the years tremendously. We can do nowadays things we were just dreaming 20 or 30 years ago. In computational kinematics, we want to try to find answers to fundamental questions concerning analysis, synthesis of kinematic chains. The notion of kinematic chain is the most important thing in my research or the most important notion within my research, because kinematic chains are in every mechanical system. No matter, is it a serial or a parallel robot, is it a wire robot, or walking, jumping machines, rolling autonomous robots, whatever. Everywhere you will see kinematic chains. And the questions we want to answer, they concern forward inverse kinematics, description of singular solutions, also workspace questions, or even synthesis questions. Such problems are very often mathematically described by systems of equations. These systems of equations contain many variables. They can be of algebraic nature, or they can contain functional elements, such as, sines, cosines, tangents, and tangent halves. And it turns out even relatively simple questions, they can become quite involved once you try to solve the systems of these nonlinear equations. So it makes sense to be a little bit careful how you establish the equations, what can be done, and very often it is very, very useful to have some geometric insight and do some geometric pre-processing before you start with the solution of the equations. So that's what I'm always a little bit sorry that I have to realize, that in engineering education nowadays, geometry has lost a lot of space, that in many universities, in many faculties, geometry is completely abandoned. And what I feel is that geometric basic knowledge is very often very, very, very useful when you want to solve kinematic problems. And I still believe that kinematics is on the basis of every mechatronic system. When you do not understand the kinematics, control will not help you to make your system run. And even, of course, it's the same with the dynamics. Okay, I want to talk about the mathematical description of mechanisms. My title is From Mechanisms to Constraint Equations. And when you look at this problem, you need essentially two ingredients. The first ingredient is you have to know which parametrization of the Euclidean displacement group you want to take. The second ingredient is the mathematical description of the mechanical device itself. When we look at first at the Euclidean displacements, many parametrizations are known. For example, the Euler angles, the Rodriguez parameters, Euler parameters, Studi parameters, quaternions. Essentially, when you look, some of these concepts like the Euler angles, the Rodriguez parameters are not so well suited for the mathematical description, because from mathematics we know that Euler angles and Rodriguez parameters have parametrization singularities, which have nothing to do with singularities of the mechanism. These are just singularities of the description. And by the way, these two concepts only confer the rotation part of the transformations of the motions or displacements in three-dimensional space. And by the way, the notion of Euler parameters, which are singularity-free, and the notion of quaternions, these are the same things, only two different names. The same is the case, by the way, with the name Studi parameters, which are parametrization of the whole displacement group, and the notion of dual quaternions. These two things are identical. So they are synonyms for the same mathematical concept. When we look at the mechanism itself, the mechanism itself can be described by vector loop equations. This is very, very often done in the past. I have seen most of the papers I get to review, they have a description of the mechanisms using vector loop equations. The other way to describe is implicit constraint equations. This is our way to describe a mechanism, and this is the purpose of this lecture, that I want to show you how we get these implicit constraint equations, and how we can handle these implicit constraint equations to solve the kinematic problems mentioned in the last slide. I am very much interested in a global description of a mechanism. That means I want to know all the poses a mechanism can reach. I want to have a global description of the workspace, a global description of all singularities in different spaces, either in pose space or in joint space. Implicit constraint equations are very suitable to do all those things. This is the reason we are using the Studi parametrization, the so-called dual quaternions. And one of the motivation why we are using this parametrization is that we can use methods, algorithms from algebraic geometry. And there are very powerful tools that have been developed within the algebraic geometry that can be used in the analysis, synthesis, and questions of mechanisms. Of course, this is a multidimensional representation because the group SC3 is a 6-dimensional group. And when you want to use this concept, you should have some idea of multidimensional geometry. Let me come very briefly to the mathematical concept. You can call this Studi's kinematic mapping. What is this mapping? The mapping is called kappa here, and it maps an element of the displacement group onto a point in a 7-dimensional space. When you go back and you have such a point in 7-dimensional space, and you map it back onto the element of the displacement group, then you get a very simple parametrization of the displacement matrix. In this displacement matrix, you see 8 coordinates. There are 4 x's and there are 4 y's. The 4 x's essentially are the Euler parameters of the rotation group, but they are written here, as you can see, in algebraic way. There is no sine and there is no cosine in this equation, and this makes it useful and usable for the algorithms from algebraic geometry. This is the basic why we are using it. Now, as you can see, a point in 7-dimensional space will have 8 homogeneous coordinates. Homogeneous means that the coordinates are the same only because of the ratio of those coordinates. This is why the coordinates are written here, as you can see in the bottom of that slide, x0 in ratio to x1, to x2, x3, and so on. These are called Studi parameters, but this is identical to a parametrization of the displacement group with the so-called dual quaternions. Within this talk, I will not use the concept of dual quaternions and dual quaternion multiplication and everything that comes with the dual quaternions, but essentially, as it has been shown in the past, in many papers and also in papers which I have written, these two concepts are almost identical. Let's come now to the most important notion, and this is the notion of constraint manifold and constraint equation. And the definition is quite simple. A constraint manifold consists of all poses an end effector of a mechanism or robotic mechanical system can attain under the presence of mechanical constraints. Essentially, this is identical to a definition of a workspace, if you wish. Yeah, so we want to know where the end effector of a mechanism can go under the presence of mechanical constraints. Mechanical constraints limit the motion of the links in a kinematic chain. It's the same that with your arm, you can reach only a limited set of poses in 3-dimensional space. And the number of, or the set of all poses is limited, first of all, by the joints you have in your arm. And second of all, by the link lengths of your forearm, of your hand, of your fingers, and so on. So this is the first thing. The mechanical constraints are therefore caused by the joints that connect the bodies, and the parameters of the kinematic chain. The sequence of these links in the kinematic chain, and this is also the case for a parallel manipulator and also the case for a wire robot or for any other system, corresponds to a sequence of coordinate transformations. In each leg of a parallel manipulator, you have a kinematic chain, and this kinematic chain can be described by a sequence of coordinate transformations that transform your coordinate system from the end effector to the base, or vice versa when you want to do the inverse notion. The mathematical description of this sequence of links transformations is done by the so-called constraint equations. When you are interested a little bit more, I have recently written an entry in the new Encyclopedia of Robotics on constraint manifolds. Okay, let's assume we have found the constraint equations. What can we do? What we can do is we can get global information. Global means all things on the forward kinematics, the inverse kinematics, the forward and inverse singularities. Very important also, so-called input-output relations. An engineer would be very interested when he puts in the mechanism some rotation, what is the end effector rotation, what is an input-output relation. But you can also do synthesis, design of the manipulator to perform a desired task. We have done this analysis with many different devices. Just a few of them are listed here. You have heard already that I have done the Stewart platform for the flight simulators, for example. There are parallel manipulators of different kinds. This is a rather simple 2 RRR and 1 RSS parallel manipulator. We have done it also together with the group in Cluj-Napoca to do the analysis of different devices for mechanical purposes. You can do it also for serial and mobile robots. We have done work on this, especially for this manipulator to do the singularity avoidance. And there is another parallel manipulator, a 4RUU manipulator, which we have analyzed with the group in Nantes. Okay, so of course now the question arises, how can we find the constraint equations? How can they be obtained? Essentially, there are 3 methods. Method number 1, if you have some geometric basic understanding of your mechanism, then you can use these geometric properties of the mechanism to find out constraint equations. I will show you an example later on. For example, what could these geometric constraints be? The constraints could be that one point of the moving system is bound to be on a geometric element, like a line, a circle, a sphere, a plane, and so on. This concept, by the way, was very often used also by Andres Kecskemeti in his dynamic system, which is called Mobile. There they have these geometric constraints and they are using it very efficiently. The second method is pure elimination. Let's assume you have the forward kinematics of a chain. This is then a parametric representation of the motion capabilities of your end effector. To get the implicit constraint equations, you have to eliminate the passive joint variables. Then you will get equations that contain the pose parameters, the Studi coordinates, and the active joint parameters. And these are the constraint equations. When you do it straightforward and use dialectic elimination, using different mathematical systems, then very often you will have so-called spurious solutions. There was a lot of fuss in the late 90s, beginning 90s of the last centuries about these spurious solutions. There is a very clear geometric explanation where it comes from and how you can avoid it. I do not want to talk about this too much, but this is a very efficient method in case the systems are not too complicated. And then there's a third method which was developed by my PhD students Dominic Walter and me, which is called the so-called linear implicitation algorithm. This is an automatic machine, because very often I was asked, we are not very well educated in using geometric properties of a mechanism because our geometric knowledge is not so good. Is there an automatic method how you can find these constraint equations? And the answer is yes. And the answer is even more. This automatic method is purely linear. So you only have to solve linear equations. And that's why we have called this linear implicitation algorithm. And it guarantees a complete solution of the elimination. And what it does essentially that this algorithm, it solves an over-constrained linear system. And I have to confess that this linear system can be very large. And it's very, very interesting. When you have a nonlinear constraint equation, this algorithm will come up with the solution to find this nonlinear constraint equation by purely solving a linear system. So essentially with computers nowadays, this is very, very simple. I have decided to show you the capability of these constraint equations with a very simple example. This simple example is a planar 3RRR parallel manipulator. You can see a model of this. This manipulator is nowadays used in many, many educational labs all over the world. And what we want to do is now we have to assign coordinate systems to this manipulator. Here you see a coordinate system, the manipulator itself. You have a base triangle. You have 3 diodes, which are connecting the moving platform with the base. What you can see is that these diodes here have certain lengths. These are the design parameters, and of course the shapes of the base and the moving triangle. Okay, so what we want to do is now we want to find out the constraint equations. Here we can use purely geometric considerations to find out the constraint equations. When you look on the right side here you see the mechanism. When you have given, let's just look at the first leg of the manipulator. When you have a given input, here the angle beta of the first revolute joint here in the point P1, then when this angle is given, the location of the knee joint, as I call it, the intermediate joint in the diode, is fixed. So this point is given when the input beta is known. Then this point on the platform has still the capability to be on somewhere on the circle. So we have a geometric circle constraint. And this geometric circle constraint can be written down very easily. You see it in complete general form here in the first equation. The entries in this equation are, you have the Studi coordinates, which are here x0, x3, y2, and y1. So they are homogeneous, as I told you. We know that the planar displacement group is only 3-dimensional. So only the ratio between those 4 coordinates is important. And then the other entries are the design parameters. For example, M and N are the coordinates of the knee point J, and X and Y are the coordinates of the point P in the moving coordinate system P1 here in this case. So these are all ingredients in this constraint equation. So now what you can do is you can specially adapt the coordinate system. For example, you can put without loss of generality the origin into the point P1 and the point P2 on the X1 coordinate. So this is now loss of generality. And when you do this, you arrive at the first constraint equation for the first diet in this equation. What you see in this equation are the lengths L1 and K1 for the diet legs, and you see a parameter U. What is this parameter U? Yeah, when you allow the input angle to rotate completely, then you can parameterize this input beta into a parameter. And here, as you see, we are using algebraic parameters. This is essentially, when you know the algebraic parameters, this is the cosine of beta, and here you see the sine of beta, and this is now a constraint equation which comprises the first leg of this manipulator. I want to emphasize that you really can now continue without assigning any design variables to solve the forward inverse kinematics and so on. But I want to show you some results. Therefore, I have decided to assign now some design variables which are written here. So this essentially, you see that the K1 is square root of 75, which is the length of the second part of the first diet, and so on. Now you can write these constraint equations, assigning the design parameters, and you have three such constraint equations. In this example, the constraint equations are purely quadratic equations, and you have to solve for the post parameters x0, x3, y1, and y2. As somebody might see, I have already done the homogenization in this equation, so you do not see the x0 coordinate. You could either homogenize by using x0 square plus x3 square equals to 1, which is essentially nothing else what you know than sine square plus cosine square equals to 1. But you could also normalize with x0 equal 1, but you have to be careful. x0 equals 0 means a 180-degree turn, and when you normalize with x0 equal to 1, then you exclude the case that the platform could be upside down and have a rotation of 180 degrees. So you have to be a little bit careful. In this example, I have checked very careful. x0 equals 0 is not a possible pose for the input parameters we want to give. And you solve this system of equations, and three quadratic equations, you would expect eight solutions, but we know that two solutions go to infinity, and so this problem of the forward kinematics of this 3RRR manipulator is essentially has essentially 6 possible solutions, and there are many examples where all 6 solutions can be real. One of the solutions I'm showing here with the input beta, alpha, and gamma 90, alpha 60, beta 53.13 degrees, which is a nice number in the tangent half, which I have taken. You get one possible solution of the forward kinematics as it is shown here. So this is the complete forward kinematics, but with the same set of basic equations. And here you see the complete set of basic equations. What is different to the equations before? Here you can see that the input parameters U, V, and W are in the equations, which means these are the tangent halves of the input angles. Now we want to solve the inverse kinematics. Inverse kinematics means that we assign values to the pose parameters, to the x's, to the y's. So we give a pose of the end effector, and we want to know what are the input parameters. Of course, this is a very simple task because you have to solve these equations for the u's and the v's, and you see in this example, the u is only in the first equation, the v is in the second equation, and the w is in the third equation. So you can solve each equation, and of course, it's simple to see that in this case, the inverse kinematic means that you have to solve the intersection of a circle with center P1 and length L1, radius L1, with a circle centered at P1 with radius K1. So you have two solutions. But essentially that means in the inverse kinematic solution, you have to combine those possible, or you can combine those possible solutions of the inverse kinematics. And therefore it's well known since the PhD of Ilyan Bonev, by the way, that you have 8 working modes, as it is called. So you have 8 possible working modes. And it's very interesting. These working modes are separated by the input singularities. So you have singularities, and I will talk about these singularities because the same set of equations also solves the problem of singularities. What do we have? We have the 3 constraint equations, H1, H2, and H3, as you have seen in the slide before. We add a normalization condition because x0 and x3 are linked somehow. Here I am using x0 square, x3 square equals to 1 because essentially this is sine square plus cosine square equals 1. So you have 4 equations, and now you can take the derivatives either with respect to the post parameters, which are the x's and the y's, or with respect to the joint parameters, which are the u's and the v's. So you will arrive at an equation of this type, which is the very well-known equation that has been appeared for the first time, by the way, in the PhD thesis of Clément Gosselin. So this is something that is very well known. So you have the matrix JO, which is the Jacobian matrix of the forward map, forward kinematics map. And you have the JI matrix, which is the inverse map. So you see in this case, the inverse Jacobian matrix is very, very simple. It has diagonal form. The other one is a little bit more complicated. Now let's solve the problem of singularities of the forward map and singularities of the inverse map. We can do it with the same equations. When you are looking for the forward singularity, then what occurs is that the parallel manipulator allows some shakiness or infinitesimal mobility when all inputs are locked. When we go back, when all the inputs are locked, here you have the joint parameters, then here you get 0, 0, 0, 0, because you have no change in the inputs. So the right part of this equation vanishes and only the left part of the equation remains. So you have to discuss the left part of the equation, J0, y dot equals 0. What this means is that you will arrive in a singularity when the matrix JO becomes singular. This is the case, at least in the first attempt, when the determinant of this matrix vanishes. From the determinant of this matrix, you will get a 5th equation. So now you have 5 equations because you still have the constraint equations, one more equation. This equation, by the way, contains all the post parameters and also the input parameters, u and v. They are still in because you are differentiating with respect to the x's and the y's. So what you can do is now you have a freedom of choice. You can eliminate either the post parameters, then you would get the forward singularities in joint space, or you could eliminate the input parameters, the parameters which drive the mechanisms, then you would get the singularities in post space. I have done it in both directions. I will show you both. And here is one result. It becomes already quite complicated when you eliminate the input parameters. Then you get a surface of degree 44 in the x's and in the y's. This is already quite complicated, and this corrects, by the way, a result of Ilian Bonev, because in his thesis he has quoted that this surface is of degree 48. That was not totally correct, but he has done it only by estimating the degree of what will come out by the elimination. Now we can do it. Our systems have become much better now, and we can do the elimination. Here I am showing a slice through this surface at x0 equal 1 and x3 is equal to 0. So you can still do this. And each point here on this slice will give you a singular pose of the manipulator. So you can compute these singularities, and here one is shown. What does the singularity mean? When you look very carefully, and here is also the answer why this surface is so complicated. In the singularity space, when you go to the poses, you cannot distinguish between working modes. So you do not know when you hit one point on this singularity surface to which working mode this singularity will belong. For example, here you can see, by the way, the moving platform here is below the fixed platform. We have chosen that x3 should be 0, which means that the manipulator is in a pure translation. But this is a singular pose, as you can see. Look carefully, but it is a mixture of red and blue case. So the case are the legs which connect the knee joints to the platform. And here you can see the meaning of the singularity. The K2 here in the red, a red K2, a blue K2, and another blue K2. These legs intersect in one point, and this one point is the infinitesimal center of rotation, which makes the possible small rotation of the end effector, so the end effector is not rigid in this pose. And by computing this degree 44 surface, we know all forward singularities in all possible working modes. The next step is we want to compute the inverse singularities. Inverse singularities you get when the end effector is in a fixed position pose, and you want to compute if the input is shaky. The input is shaky. You can always demonstrate to your students in the following way. When you have your arm in a stretched position, then you are in a singular pose for your arm, because here you could go from elbow down to elbow up of your manipulator. So this is an input singularity. Because of the simplicity of the determinant of the input singularities of the diagonal form, you can see that the determinant will factor into 3 parts. The 3 parts, completely general, are written here. By the way, these are the input singularities for all possible designs of this manipulator. There is no design parameter assigned here. So you can simply assign the parameters later. And when you do it, I have shown it for the last of the three factors. The last of the 3 factors is the simplest, but now you can have a simple geometric explanation. You assign the design parameters, and you immediately find out that this last equation factors into 2 parts. And these 2 parts have very, very obvious meaning. First of all, geometrically, these are 2 hyperboloids. When you are on the smaller hyperboloid, in this case, this means that one of the legs, and you compute then the pose which belongs to the solution of this equation, then you will see that one leg is stretched. It is in a singularity. When you are on the broader hyperboloid, then this means that your leg is in a folded position, which is also an input singularity. So in between those two is the possible workspace of the manipulator, which is singularity free. Very simple explanation what you get with these constraint equations. But of course, you could also have the idea that you want to have the singularities in joint space. Maybe the engineer would be more interested to know what are the dangerous inputs. What are the dangerous inputs which I have to avoid? Then what you have to do, you eliminate the post parameters. You arrive again at the complicated surface. In this case, it's a surface of degree 28. And when you take a point on this surface, you will arrive at the singular input singular pose of your manipulator. Okay, let me go on. I want to show you also some serial things. And I've seen I'm almost at the end of my talk, but Martin has allowed me to be a little bit longer because he has told me that two presentations of the next session are missing. So I hope you do not complain. So if somebody complains, please let me know. Send me immediately a chat and tell me that I'm too long. Serial mechanisms. I want to show you how these methods with the implicit constraint equations also work in serial mechanisms. Here we have a closed kinematic chain, which is very well known. It's Bricard's orthogonal chain. The Denavit-Hartenberg parameter of this chain you see here listed in the table. So we have no offsets, as you can see. The joint angles are all 90 degrees. And we have these distances between the axes of the revolute joints. You will get an over-constrained 6R mechanism, which was already found in 1896 by Raoul Bricard, when you have the condition between the joint distances, which fulfills this alternating quadratic equation. So when this is fulfilled, then you will have a 1 degree of freedom motion of this chain, and this has been used by a Swiss company to make a heavy-duty shaker mixer, as they call it. This is a mixer that is used in chemical industry. Okay, the question is now, what happens when we do this with our implicit constraint equations? It's quite easy and straightforward to find this set of equations that is completely describing this orthogonal chain. What do we have? The parameters in these 8 equations that you see here are the Studi parameters, the x's and the y's. And there are 2 parameters in which describe the chain. This is the V1 and the V6 in this equation. So essentially the V1, for example, you can see here, and the V6 you can see here. Why have we done it like that? The V1 is the input parameter, and the V6 is the output parameter. It means when you rotate, when you make a motor in the first revolute joint, then this V6 will give you how the output rotation will be triggered by the input motion. When you take these systems of equations and you have an algebraic manipulation system like Maple, for example, what I was using here, then you can ask for something what is called the Hilbert dimension. The Hilbert dimension tells you something about the dimension of the solution space of this set of equations. So for example, when the Hilbert dimension is 0, then this means you get some rigid configurations of this mechanism. When the Hilbert dimension is 0, what I said, then you have some, when it is -1 by the way, then it would mean that it is very, very, very rigid. Yeah, it's even more rigid than it is when it is 0. But when Hilbert dimension is 1, then it means there is a 1 parameter set of solutions. And it means that you have a 1 degree of freedom in the kinematic chain. Here the Hilbert dimension tells us it is 1. And now you can use algebraic geometry. You can compute something that is called the Gröbner base. And you can do it, for example, as I did it here, with a so-called total degree ordering. I cannot explain everything on this, but I will give you a reference when you're interested how you want to do that. Here you have to put an ordering in the unknowns which are in the equation. And when you do the ordering in such a way that V6 and V1 are the last two, then the system will come up with one last equation. And as you can see, this is the complete input-output equation of this mechanism. And it is of degree 4. It is a biquadratic equation, if you want to say it more clearly. This is already old stuff, and it is already in the thesis of Martin Pfurner, who is known to most of you. Okay, and there is a new reference when you are interested in mechanism, constraints, and singularity. We have done a book going out of the Singularity School, which was organized in Linz a couple of years ago, and it is in the book series of GISM, International Center of Mechanisms. Marco will be quite happy, I hope, at least. Okay, I will show you how you can apply this to spatial parallel manipulators. Here is one manipulator that is discussed a lot in the community. It's a 3-RPS manipulator. You have 3 legs, revolute joint, prismatic joint, spherical joint. The attachment points are here, in this case, on equilateral triangles. So you have essentially two design constants. This is the radius of the circumcircle of the base triangle and the radius of the circumcircle of the moving triangle. This is taken from the thesis of one of my students, Josef Schadelbauer, in Innsbruck. But it was also used a lot by Latifa Nourami, maybe known to some of you. She was a PhD student in Nantes, working with Philippe Vongère. She has transformed this manipulator into a medical device for ankle rehabilitation. So the kinematic description of this manipulator is in this set of equations. So you see essentially the design parameters H1 and H2 are in, and all the other things. From the equations, you see immediately from the first equation that the manipulator has 2 working modes, either x0 equals 0 or x1 equal to 0. You can discuss it from here on, and everything which was necessary to feed the controller of the ankle rehabilitation system is derived from this set of equations. I want to be a little bit more clear how it is done by using another example, and this is the so-called Tsai UPU parallel manipulator. This manipulator was designed several years ago by Lung Wen Tsai for the purpose of designing a parallel manipulator which has purely translational motion. And Lung Wen Tsai was a very good designer, and he has proposed this design. Again, equilateral triangles, again, 2 design constants H1 and H2, circumcircles of these equilateral triangles. But here you have now a U-joint on the base, and the Tsai manipulator is characterized by the fact that the first revolute axis of the base cardan joint is tangent to the circumcircle of the base triangle. And the same is the case with the 4th revolute axis, which means the second revolute axis of the cardan joint on the platform. They are also tangent. When you switch the sequence of these joints, then you get the Seoul National 3 UPU manipulator, which was designed by Frank Park and his group. which has a total different kinematic behavior. So let's look at the constraint equations of this manipulator. They are very interesting. I do not want you to look very carefully at the equations, but just look at the first four equations. In these four equations essentially geometrically mean that the intersection points of the axis of the second Cardan joint, they always have to stay in a plane. So that's why these equations are so simple. They are bilinear equations. As you can see, there is no square in these equations. And this is the key to the analysis of this manipulator, which was done by Dominic Walter, one of my PhD students later on. The second three equations, they comprise the fact that the distance between the centers of the first Cardan joint and the second Cardan joint are governed by the prismatic joint, but these are so-called distance equations. They are a little bit more complicated. It's very important to see that the first four equations do not contain the input parameters. Input parameters are the D's, these D's here. They are only in the last three equations. So it makes sense to discuss it from algebraic point of view. You can write it as a ring of equations, and the ring has the design variables, the input variables, and the post parameters, the study parameters. So you have 8 such equations, and it makes sense to discuss at first only the first 4 equations, because one can expect that you can see already from these equations the design idea of this manipulator, namely that it has to contain at least a component where the manipulator shows a purely translational motion. And what we have done here is something that is called primary decomposition. Primary decomposition means when you have a set of equations, you are looking if it is possible to decompose this set of equations into smaller sets of equations. We can expect it here. And here the primary decomposition shows us that we have 5 different components. The first component here, which you see here, is the component which will give us the motion for which the manipulator was designed by Lung-Wen Tsai, because it tells us that the x's are 0, and where is my mouse? It tells us that x1, x2, x3 are 0, which means that you have the identity matrix in the rotation and only the y's are not 0. The y0 equals 0 is necessary. Otherwise, the Studi equation would not be fulfilled. But you have 4 more simple components and 1 component which is highly complicated. It's a 3-degree of freedom motion. There is a 6th component which always comes out in kinematics, but this is not allowed. This would give you the rotation matrix filled up with only zeros, and this is not possible. So we have this first information coming from the first 4 equations. We have to add the other equations, so the G5, the G6, the G7, and the Studi equation. We have to take the union of those sets. So, but now the forward kinematics can be done for each component separately. Maybe you do not totally understand what does it mean when you have an equation and you split it into components. Think of the following simple possibility. Think you have an equation of degree 2 in 2 variables. And this equation should be of degree, in 2 variables, and the degree of the equation should be 3. Then it could be a curve in the plane of degree 3. But it could also happen that this equation splits into 2 parts. into a linear part and a quadratic part. So it means it is a line and a circle. So this is essentially what is happening here. So this equation of a higher degree splits into smaller parts. And the meaning of these smaller parts, of course, has a meaning for the forward kinematic solution. So when you take, for example, the complete set using the first component, then you will see that you will get two solutions of the forward kinematics. For an engineering, totally obvious. When you are in the purely translational mode, of course, you will get the forward kinematic solutions, which is mirrored with respect to the base. So you get two solutions. But in the third component, you get 4. In the fourth component, you get 6 solutions. And in the fifth component, you get 64 solutions, which means in total, this manipulator has 78 theoretical forward kinematic solutions, which is much more complicated than the Stewart platform, which has 40 solutions. So a special case comes up when the legs are of the same length, then you get different numbers. So what is the meaning of these different components? First component is the purely translational mode. The second component means that you have a twisted translational mode. The platform is upside down, and then the legs are crossed over. Yeah. Then you have a planar mode. So it can be folded down such that you have a purely planar motion. Then you have an upside down planar mode, and you have a general 3 degree of freedom motion, which is far from the translational mode. For example, the transformation mode, the transformation matrix for the translational mode, immediately you get, it's like this, which is each of the components will have singular poses. From the equation, you can compute all the dangerous positions in each component. I show you just the singular ones for the translational mode. So once you are in the translational component and the input parameters fulfill this equation, sorry for the double, there should be only one, yeah. You fulfill this equation, then the manipulator is in a singular pose. You can plot this singular surface if you want in joint space. And it looks like this. By the way, it's a very famous surface, which is very well known in algebraic geometry. When you go to the planar mode, you see the singularity surface splits into essentially 5 parts. There are 3 planes, which you see here, and 2 surfaces. F2 and F3 are these 2 surfaces. F1 is just a constant. So these are the singularities in the planar mode. And now you can ask the following question. Is it possible that you assemble your manipulator, for example, in the translational assembly, yeah, where you want to have this pure translational mode? Is it possible that you come into a pose where the manipulator can go into another component? Meaning, this would be very bad because gravity, for example, could force the manipulator to go down into the other mode, and then you completely lose control of the manipulator. And the answer to this question is here very fast in this table. And this table shows you several numbers. Here you have the different components. This is the translational component, upside translational. This is the planar one, upside planar one, and this is the general mode. So for example, this means from the translational mode, it is not possible to go into the upside translational mode, which is quite obvious. You have to disassemble, turn the platform around, and then you reassemble the manipulator. But it is possible to go from the translational mode into the planar mode and also into the general mode. And the number 2 means that you have a 2-dimensional set of input parameters where this is possible. So this is the meaning of this table. We can also use it for the inverse kinematics of the general 6R. How are we doing it when you have the forward kinematics of a general 6R chain? This is the forward kinematic map. Here you have rotation about the first revolute joint, coordinate transformation to the second frame, and so on and so on. And you assign values to the end effector. So you want to know what are the input parameters which fulfill this equation. What we are doing essentially is we are splitting the manipulator in the middle. So essentially what we have, two chains, a forward chain and a backward chain, essentially like your two arms. And the solution to the inverse kinematics means that you have to shake hands. Essentially, you can do this. What you have is you have the forward chain and you get the constraint manifold of the forward chain. You get the constraint manifold of the backward chain. And it turns out that these constraint manifolds are two one-parameter sets of hyperplanes in this high-dimensional space. So essentially, the nonlinearity comes from the input-output angle, which we will keep in. And I have to tell you, the system of equations is now so simple that it has been implemented by one of the PhD students named Angerer, and he has shown that the implementation yields a solution of the complete set of the inverse kinematics in 1 millisecond, which is real time, in 99.8% of the cases he had tested. So it means this algorithm can be really real time implemented to get all solutions. We know 16 solutions, but this set of equations which we get allows now also the answer, can we find designs so that all 16 solutions are real? And this has been done in another PhD thesis, and Matthias Brandstätter found many designs where the manipulator has 16 real solutions in a quite large part of its workspace. An example is shown here. By the way, this manipulator has been built with so-called Schunk modules, and it has been experimentally verified that these solutions all can be attained, all configurations. Sometimes it's not easy to go into this configuration. Sometimes you cannot, you have no motion to go from one configuration into the other. You have to reassemble the manipulator in practice. It is also important to know all the solutions of the inverse kinematics. We have a paper in a journal where we are showing that it is really dependent which solution of the inverse kinematic you are using for a starting position for fulfilling a certain task. So let's assume you have to do a welding seam, and it is really a difference with which configuration you start in the time you are using for the welding. And let's assume you can reduce the time of some task by, let's say, a few tenths of a second, and you have to do it 1 million times, then it matters in which configuration you are starting. That's all what I wanted to say in this talk. I thank you very much for your attention, which is 15 minutes longer than I was intended, that I was allowed, but I hope it was interesting for you, and I could have shown many more examples. Thank you very much.
Thank you very much, Manfred. Amazing presentation. I have some question about the modes. You can change of mode in some case, very few cases. Sometimes you have multiplicity. That means the set of the table, multiplicity of possibility to change the mode. And you can choose for a given task using some metric, which is the more convenient mode? Can you use that? Can you do that?
Yes. This is, let's say, this is the positive answer to this. Yeah. So you have Lungwen Tsai, for example, has designed this manipulator for purely translational motion. Yeah. But what we were showing is that the manipulator, and this example already has been shown for the UPU manipulator many years ago by Ilyan Bonev and Dimitar Zlatanov for the Frank Park manipulator for the 3 UPU, which has a different setup. Yeah, and but you could also think, as you were mentioning right now, this could be an advantage because you have different working modes of this manipulator. So you have a purely translational, and you could have a manipulator which has a second working mode, which is purely spherical. And you can have one working mode, which is a very general 3 degree of freedom motion. And by this analysis, we can tell you exactly the poses where it is possible to move from one operation mode into the other one. So this analysis is possible.
Okay, you must combine an optimal control problem, for instance, to lift away with a robot and change the mode to lift from the floor to another position very far from the workspace, for instance.
Yes,
you must combine your inverse kinematic algorithm with change of mode and also with the dynamics and
yes,
so on.
of course. Yes, of course, you're absolutely right there. I was a little bit mentioning it. Of course, the dynamics will play a role when you are in a pose, yeah, because you always will have gravity, yeah, and
yes.
Maybe gravity will force your manipulator to go into another mode and not to stay in. Maybe the translational mode in this pose is so stable that it will not fall automatically out of this mode, yeah. So there's no automatic in it. And we haven't done any dynamic analysis, yeah, concerning this question. It would be interesting. Yes, it would be interesting.
It will be more complex. Okay, Juan Antonio.
Thank you, Manfred, for the very interesting talk. I have 2 questions. One is a very simple one, and is more didactic on you chose a specific diagram, and then I'll go into a more philosophical right after that. So the first one is, I'm quite puzzled on your slide 15, and you don't need to bring it. I'm just, this is the one where you showed on the 3 RRR, you showed the singularities, and you showed the fact that in one of the assembly modes, the 3 distal links will intersect at a common point and create a singular configuration. My question is, and it's more a didactic question, why is it that you chose to show one where you're actually, the manipulator itself is not in the configuration? You're trying to show that the alternate leg configuration or assembly mode is in the singular configuration. It's more a didactic question.
Yes. May I answer the didactic question at first?
Yeah, please go ahead. Yeah.
The question is not only didactically, it has a theoretical background. Yeah. And I was puzzled about this because I did not know why is in the case of the 3RRR manipulator, the forward singularity surface so complicated. Because in the case of a 3RPR, which is the usual one, yeah, we are using, yeah, the singularity surface is just of degree 4. And I did not understand for a long time. And I tell you, I was the reviewer of Ilyan Bonev's thesis. And at that time, we had no idea about the degree of this surface. It was only suspected to be 48 by Ilyan. Yeah. So I was puzzled, and I tried several configurations, and I do not know up to now what I have to do that I stay in a desired working mode. So even when you wish that I take 3 red legs, yeah, and do not mix it with the blue ones, yeah, I have no idea. There's no idea. There's no didactic behind it. It's just I have taken one point on the surface and I have computed, and then I realized, okay, the system is mixing the working modes, and this would be an open question, and I do not know how to answer this. So it's more than didactic.
It goes much deeper than I thought. It was not a choice for your slide. It's actually an actual problem.
No, it was showing you my own failure.
And I didn't mean to point it out, I honestly. So, and the next one is more philosophical. And since we have so many people here, maybe quite of interest, it struck me at the very beginning, you started saying that we have in all engineering programs, we are now missing the geometry side. And I can tell you that in our program here, we moved from 5 years to 4 years. This was about 15 years ago. We used to have a 5-year program, now we have 4. And when we removed, about 10 courses had to be removed. One of the courses that was actually 2 of the courses that's what were removed. One had half of it was geometry, and the other one a full course on descriptive geometry. Gone, completely gone. So why do you think that has happened? So I know how it happened in our case, and I do as a roboticist, as I do, you know, we do kinematics in my group. I miss it. I really have to start from scratch with in my robot kinematics course that I teach in the 3rd or 4th year. And some of the components they are missing. So why is it that we in engineering have lost this?
Okay, I tell you, I was struggling my whole scientific life with this shortening of the geometry within the engineering courses. I tell you one argument, which is always used by, I say, by our enemies, yes? They are saying, now we have the CAD systems, and the CAD systems will solve all these geometric problems. But this is one of the biggest mistakes you can have, because you have to use the system with a geometric knowledge. When you do not have geometric knowledge, you will just trial and error. And it's very interesting to me. I have observed it almost my whole life. The students are willing to spend hours and hours using trial and error methods, and they do not listen to some teacher who tells them how to use it in a good way. Yeah, do it in like this, do it like that, and then you can play with your new knowledge. And we have made mistakes. This is the second one in the descriptive geometry course. Too many of our colleagues have still done it in the old-fashioned way, using paper, pencil. It's very important for the engineer to do it with paper and pencil once you are in the design process. But when you're in the refining process, nowadays, you have to use the computer. So what we have, and I tell you my philosophy, we have in descriptive geometry, it's no longer called descriptive geometry, by the way, in our university. It's called geometric modeling, visualization, and CAD. So these are the important things. Yeah? Geometric modeling of design is a very important process. You know, modeling is always the most difficult part when you want to design something new. And transferring a model into a mathematical model is even more difficult, yeah, because there you have your visualization and so on. In the other way, the purpose of my lecture was to show you one possibility, and it's not the only possibility, how to go from a mechanism to the mathematical description. It's only one possibility. I'm not claiming that I can solve everything, but it's a pity, yes, you are right. The basic geometric knowledge is gone from engineering schools. It's not the case in my faculty. Yeah, we still have it.
I guess you managed to have a a stronger weight in those courses not being removed. I lost that battle many years ago. I wanted to keep it. It was one of the courses that I taught, but it happened.
Yeah, we can discuss it. What is, let's say, the power you have. I was dean in the faculty, so they do not take away the courses of the dean.
I was only an assistant professor at the time, so yeah, I had absolutely no weight.
No, this is maybe making fun of it. There's more behind it. Yes, we had to change the complete curriculum of our courses, and everything is done now with the means of the computer. But when you have the computer, I have to tell you, we have many more objects, geometric objects, than we had before. Think of just, we have all these freeform tools now, these Bezier curves, the B-spline curves, the surfaces, you have the blending, you have all these things we could not do. We can do intersections now between surfaces in 3 space and so on, which we never were able to do by hand. So there is more in it. And additionally, what is new, and this is something I am missing totally in the engineering community, is that we have transformations. Transformations mean you can look at your object from different points of view. This is the viewport transformation, but you have also transformations within the object, which is called parametric construction. And you have to understand very, very well the geometry, that you use these tools sophisticatedly and not playing, yeah? Because our time is limited. Our education time is very, very limited. You said you have changed from 5 years to 4 years. This is why, this is because industry wants to have this, the finished students earlier, and they should have a better knowledge, yeah? So everything has to be more. Like in our community, you have to have more papers, you have to have more talks, you have to more keynotes, and then every year we should have more, yeah? That's the advantage of being a retired person. I do not have to have more.
That is not comfort for me.
Yeah, it's not comfort for you, yes, but I'm still fighting for this, I tell you, quite frank.
There is some.
Thank you, Manfred, for your words.
There is another question from Daniel Martins.
Two questions, but very. One is the interesting part that you say that the study and dual quaternions parameters are the same. Well, I have to admit that I never heard this before. Well, I noticed that it were the same, but I was curious by the fact that I would like to know if his study had the inner algebraic structures like dual quaternions, like we do quaternions today. This is one question. And the second one is that I read about some other kind of SE3 representations using other kind of Clifford algebras different from dual quaternions, like I don't know, octonions and other types of Clifford algebras. What's your opinion about it?
Okay, the first question is, for sure, Studi himself knew about dual quaternions, because the dual quaternions are older than, and essentially he was using this. He never himself, he never talks about dual quaternions, but essentially he is using the concept. He's using the concept. The only thing is, and essentially when you look, the dual quaternion multiplication, using the multiplication as it is done with the epsilon square, where epsilon square is equal to 0, is essentially the same as matrix multiplication. And you can go directly from one to the other. Yeah, so there are mathematical subtleties in this. Yeah, so I'm happy that no real mathematician is listening to us right now. I know if John Selig would be here, yeah, he would have maybe some criticism to what I am saying. Yeah. So of course there are subtleties, but when you look in his book, you can see clearly it is very related. This is the first thing. Yes, you were asking, are other Clifford algebras maybe useful? I don't see that octonions are very useful. The reason is the following. The SC3, yeah, has a special structure, yeah, and this special structure requires the epsilon square equal to be 0. You can, of course, discuss other Clifford algebras. So maybe you have realized when Martin introduced me, he has told you something about my PhD thesis, which is on screws in flag space. Yeah. This flag space is a non-Euclidean space. So when you want to do kinematics in a non-Euclidean setting, you have different algebras. The different algebras, for example, they can be done in the following way. The epsilon square, yeah, can be 1, -1, or 0. And Studi himself, yeah, by the way, has written a long paper on all these possibilities you have. Unfortunately, it's in German. Yeah, it is on these transformation groups and all these possibilities with the epsilon. He calls it alpha, beta, and so on. So there are other, but they lead to non-Euclidean geometries like hyperbolic geometry, elliptic geometry, and so on. I don't think that it makes sense for an engineer to study these non-Euclidean geometries, but for a geometrician and a mathematician, it can be very interesting because you get a wider point of view, what is happening. Yeah. For example, you can do also kinematics in a projective setting, purely projective. You say transformation matrix is only linear. You know what happens? Instantaneously, you have 3 centers of rotation at any time because a general matrix in the plane has 3 eigenvalues. And the 3 eigenvalues, these are the centers of rotation and so on. So there are many other possibilities.
It's clear.
But I see there's another question by Sophia.
Sophia.
Thank you.
Please. This is the last question, Sophia Larrota.
Thank you. I have a question, Professor, regarding your comment about the geometry classes. If you had to advise a student who may have limited access to those classes you just described, what topics, concepts, and literature would you recommend for independent study?
Okay.
Nice question.
Yes. You know, we all, during the COVID crisis, had to revise our teaching concepts. I'm no longer teaching descriptive geometry because I'm retired, but my successor and the group in Innsbruck, they have developed a complete set of geometry tools with videos, with instructions, where the students can go step by step through the videos in the CAD system, and they can learn by themselves. But this is not the only way. It's very important that you have then consulting hours for the students where they can talk to the instructor, because otherwise what will happen is that the bureaucrats in my university and your university will say, okay, let's make an online course and we sell this online course to everywhere in the world, and we do not need the teachers at our place anymore. So you should not replace yourself by doing videos, yeah, and instructions. We could talk hours about this problem. I know, are you teaching geometry?
I am just a student. I just want to ask.
Yeah, this doesn't matter. Doesn't matter. It's not. I can see it with my granddaughter. It's really a burden. to sit in front of a computer and not to see your colleagues and not to see your professor. You cannot ask questions and so on. So I think a mixed form, yeah, of online and presence teaching is maybe a good way in the future.
Thank you, Sophia. Thank you, Manfred, for this trip all along the geometry and the constraint formulation and the real way to interpret the constraints in terms of the physical meaning and the mechanical meaning, and also the mechanical challenge. So there are some open issues to solve, very interesting for the technological development of robotics and mechanics. Thank you very much, Manfred. All the people can contact Manfred through us. So really,
thank you very much, Martin. Thank you.
It was very interesting. A long talk, but very amazing and relaxed talk. So thank you very much. And we will do a break. So Juan Grijalva will start the next block at 11:45. So let's take a break. And give an applause to Manfred also. Thank you.
Thank you.
So see you in 15 minutes. Juan Grijalva, please, you must be available. Then Rogelio Ecker, then Fabricio Silva. Mauro Vaquero canceled the talk. And then after Fabricio will present Glauco coding. Please be ready. Thank you. Yes, also. No. Welcome back. We are now starting the control of mechatronic system session. Rogelio Ecker from Argentina will be the chair. Please, Rogelio.
Okay, thank you, Martin. Good morning, everyone. This is the session for control of mechatronic systems. And now we are going to have a presentation from a student, Juan Gabriel Guerrero Grijalva, and the title is A Synthesis of Retractable Roof System Based on Spherical Scissor-like Elements. Welcome, Juan.
Thank you, Professor. Firstly, thank you for everyone for attending my presentation. I'm going to present the paper Synthesis of a Retractable Roof System based on spherical scissor-like elements, as the professor said. The authors are Professor Daniel Martins, Professor Edson De Pieri, and, well, as the professor said, I am Juan. Firstly, I'm going to introduce the spherical scissor-like elements. We can see on figure 1 the conventional scissor-like elements on the left side, which are also known as pantographs, and are two bars connected to each other at an intermediate joint called pivot. And on the right side, we have the spherical version of the scissor-like elements. Well, as I said in a paper that I showed before, it's not possible to speak about the advantages or disadvantages of each version of scissor-like elements. These ones are going to depend on the application of that these ones are going to have. The main difference between these two kinds of spherical of scissor-like elements is that the conventional scissor-like element slides over a planar geometry On the other hand, the spherical version slides over a spherical geometry. We also can see the isometric view, the front view, the side view, and the top view of both versions. Firstly, we considered to develop a kinematic analysis of the spherical dual quaternions. It is a novel approach presented in the literature. Well, I'm not going to speak a lot about dual quaternions because, as we can see in the presentation of Professor Manfred, it's a very extensive topic. But well, in our university in Brazil, in Santa Catarina University, we are studying a lot about dual quaternions because it was possible to develop sophisticated tools in the kinematic analysis and in control area too. Well, we have the dual quaternion that represents the geometry of any scissor-like element. Well, the spherical version of a scissor-like element. In this case, we are using the spherical scissor-like elements to assemble a retractable roof system. So in equation 3, for example, we can use it to compute the length of the area covered by the retractable roof system. On equation 4 can be used to compute the input overture of this mechanism. On equation 5, we can use to compute the spherical scissor-like element bar length. And using equation 6, we can compute the height of the retractable roof system. As I told you, we have developed sophisticated tools. For example, in figure 5, we have the workspace of a point located on the one link on the mechanism, and on the right side we have the area that would cover the retractable roof system. Well, nowadays almost all the retractable roof systems includes a control system, turning all this kind of retractable roof system into mechatronic applications. In this case, we are using a mass spring damper model. It was a strategy to simplify the dynamic modeling of this kind of systems, because scissor-like elements structures have many joints and links, and it's very complicated to develop a conventional modeling, dynamic modeling, for example, using Newtonian approach or Lagrangian approach. We tried it and it's very extensive. So we decided to use a modeling using a mass spring damper model. Then we developed a identifying procedure. So we have the mass spring damper model, and we identify the parameters from a dynamic simulation. In equation 7, we have the parameters of the mass spring damper model, that is the spring and damping coefficients. M is the mass of the model. F is the input force that is supplied by an external actuator. The matrix C is 1 and 0 because, well, we have two states. The first state is the position, and the second state is the velocity. In this case, we are interested in know the position of the retractable roof. So this matrix is 1 and 0. And omega is represents the uncertainties in the retractable roof system. We consider it uncertainties in this kind of system because, as we know, all the roofs are in contact with the environments, with raining, with humidity, with external factors, and the lubrication in the joints can vary easily. For this reason, we consider it a completely lubricated condition and a poor lubricated condition. And these are the uncertainties of these values are going to oscillate or vary between these conditions. In the last slide, I showed you the mathematical model, and now the control algorithm that we use is presented in this slide. The main feature of this algorithm is that it offers the possibility to allocate the poles on the S-plane in an arbitrary regions, as we can see in the three S-planes presented in this slide. And this gives the possibility to obtain arbitrary performance, for example, to avoid overpeaks in the control outputs, to set a settling time in the response of the system. In figure 7, we can see a comparison of many performance using different tuning parameters. As I told you, by allocating the poles in specific regions, we can obtain different characteristics in our performance of the retractable roof system. Now I'm going to show you an animation video of this mechanism. In this video, it represents, for example, it starts off a deployed condition, and it starts to undeploying in the time. For example, it represents a complete closure of the roof system, and then it retracts again to the beginning. Well, this is all. Thank you for your attention.
Thank you, Juan. Very interesting presentation. If there are any questions. Okay, Juan Antonio, go ahead.
I guess I couldn't pass making a question. So the idea here is, this is an example, I guess, that you presented, the roof-like structure that you presented. I'm assuming that based on that example, you have the advantage that you have gravity helping you as you essentially extend that roof. You have gravity helping you to take what normally is the worst, I guess, the one of the reasons why scissor-like mechanisms are not used as often, that play in the joints is propagated quite significantly through the kinematic chain. So is that something of concern here, or it isn't?
Yes, it is. Well, firstly, one of the main differences compared with using conventional planar scissor-like elements, we already presented a paper using planar scissor-like elements, a folding roof structure of using planar scissor-like elements. And we used it, I guess it was 30 or 50 scissor-like elements to develop a folding roof structure to cover the same area of the roof presented in this paper. In this case, we are only using 4 spherical scissor-like elements. I only want to highlight that one advantage is that I could use less scissor-like elements than using conventional ones. And well, other reason is the gravity, of course. We realized that some nowadays retractable roof systems, for example, in Santiago Bernabeu Stadium, the time to fold and deploy the folding roof, it lasts about 5 hours. So it's many time. So we employ, for example, many factors like gravity to offer a faster approach of a retractable roof system. Yes, it was. reason.
Okay. Professor Husty?
I have just a small remark and a small question. Why are you using dual quaternions for spherical mechanisms? Is there anything you can forget the epsilon, yeah? Because quaternions are enough, because the other parts are all zero. You have no translations, so you do not need, essentially. It just complicates your computations. You can forget it, yeah? This is my remark, yeah. But essentially, what do you want to do with the quaternions? What is the purpose? You can describe something, but what do you want to compute with the? It was not clear to me.
Okay, firstly, of course, we have submitted many papers, and the reviewers have told us the same than you. Why are you using dual quaternions? Well, the main reason is because in our laboratory, we are using dual quaternions for everything. For multi-body systems, we are doing many times, of course, we can avoid it. But we're trying to use it in many fields. For example, in control, we are using dual quaternions. In kinematic control, we're using dual quaternions. And well, the main reason is that we are trying to apply as most as possible dual quaternions, because as I told you, in our laboratory, we have developed many tools.
That's not what I'm commenting. I'm commenting in this case, yeah. You do not need the dual, yeah. You use quaternions. This is fine. I like it. Yes, I like it that you use it, yeah. But in this case, the dual is not necessary because it's purely spherical. Essentially, the correct word what you are using is Hamiltonian quaternions.
Yes.
Yeah, this is what Sir Hamilton has developed at first. Yeah, these are Hamiltonian quaternions. The dual epsilon comes only in when you also have the translations. In mathematics, we would say it's a semi-definite metric and so on, but this is not necessary here. I always ask my students not to, let's say, overwhelm other engineers by using words which are not necessary. That's my only criticism. Everything else is fine, yeah. So.
That's true, and well, as we know, dual quaternions, we can use only translation too, and we can use only rotation or both at the same time. And yes, that's true, Professor.
But here you have only rotations, yeah?
Yeah, that's true.
It's a purely spherical mechanism, as you say in your title, yeah?
Yeah, that's true.
Okay, for a matter of time, we need to continue with the next presentation. Please, Juan, I need you to stop sharing the presentation.
Okay, ready.
Okay, thank you. Then I believe my next presentation is my presentation, and I will introduce myself. Well, my name is Rogelio Hecker. I'm working in the University of La Pampa in Argentina, and I'm going to present closed-loop compensation of linear deviations in ball screw drives. Well, as you know, the ball screw is a precise element that is used in many precise machines. The ball screw in general, well, they perform in a linear way, but we can achieve different kind of movements according with the machine design. Here we have an schematic representation of a linear feed drive with a ball screw, where we have the electric motor, the ball screw, and the carriage or the table. And in the figure, in the block diagram, we can see that the typical control strategy is collocate control. That means that in general, we are using the rotations displacement to feedback in our controller system. The reason for that is that in this kind of control, you can achieve high bandwidth because as you can see in the body plot, the system in theory, it doesn't get unstable for high gains. That's in theory. Then this kind of configuration is the one most used in industry. And after that, we can see in the block diagram that there is a relation between the angular rotation and the linear displacement that is given by the gear ratio of the ball screw. But in reality, what we have here in between the rotational measurement and the linear displacement is a transfer function where we have the, for example, we have the vibration mode of the screw. And also we have some perturbations like the thermal expansion of the screw. Then a second way that we can close the loop is using directly a linear scale. In this case, all these dynamics, like the vibration of the ball screw, are now into the closed loop. Then this is an advantage and this is a problem at the same time because the design of the controller is a challenge. In general, with this kind of controller, we cannot get a high bandwidth. Then the idea was to combine both controllers or both ideas. Then here is our proposal. Our proposal first, we are implementing in the collocate strategy. That means that we are using the rotational encoder of the motor. We are implementing a sliding mode control. Here we have all the equation for the sliding mode control. I'm not going into this equation because it's already known, this kind of controller, and it was implemented many years ago and still implemented on these times because it's a robust kind of control and is giving a very good performance. Now, our proposal is, as you can see in the block diagram, we are taking a linear deviation. A linear deviation is the difference between the rotational measurement on the encoder and the linear measurement on the linear scale. Then there we will have a difference, linear deviations, and we are feeding back this linear deviation to modify the reference to the rotational motor. The only controller or transfer function in this case we are adding in the outer loop is a filter. This filter, as you can see here, we have the expression, general expression for this filter. It has some order n and a corner frequency fc. We need to tune these parameters in order to get a stability of the whole system. There is a tuning process, of course. First, we tune the sliding mode control to achieve low errors at the rotational encoders. This is mostly this is a try and error process experimentally, and we can get good result with a high bandwidth at the rotational encoder. And after that, by simulations and looking at the phase diagram, the body diagram, we can tune the filter for the new outer loop under nominal condition and non-nominal conditions. This is important because when we put some extra load on the table, or when we move the table from one extreme to another, the system changes, and then the dynamics change. Then we made the tuning of the filter to achieve good results in several configurations. We found that the filter, that we have the expression right there, we need an order of 6 and a corner frequency of 35 Hz in our system to achieve good results. Now going directly to the results, first we implemented only the sliding mode control. That means only with the rotational encoder to have a comparison with the new proposal. We can see here in the second graph that of course the angular tracking error is very low. But when we are looking at the linear encoder, we can see that there is a considerable error between, it gets maximum 35 micrometers. We need to analyze a little this graph because we can see a long wave error. This is metric error. And we can see also a high frequency error. This comes mainly from the pitch error of the screw. And also we have at the beginning and the end and at the middle, we have some error that comes from friction. After we implemented the additional control loop, that is to compensate the linear deviation, we can see that the linear tracking error is reduced. Mainly, it was eliminated the long wave geometric error. We cannot eliminate the pitch error and the friction error because we have a low pass filter. Of course, this low pass filter was tuned for a stability purpose. Then we cannot increase the bandwidth of this filter to control this error, to eliminate these new errors. Another interesting result is what is probably the most important result. Here, the table was static. In the previous experiment, of course, the table was moving following a trajectory, but here the table is static and we want to maintain the table at a given position. Then we start hitting the ball screw, and we can see here in the second graph how the motor changed the angular position in order to maintain the table at the same position. It is an important movement. Here is expressed as a linear displacement, but the motor has to move more than 100 micrometers in this case to maintain the table in the same position. Then in the first graph, we can see that the table is at the same position, of course, with the normal vibration that we saw for this kind of controllers in the previous slide. Well, the conclusion are that we were able to implement an outer loop to compensate the linear deviation. And we were able to eliminate the long wave geometric error of the screw and the thermal expansion of the error. The outer controller was tuned for nominal and non-nominal conditions, which is important for practical application. And probably the most important conclusion is that this outer loop can be implemented in any existing control system, of course, with access to feedback and control signals. We have to take in account that this is an application paper. The proposal is quite simple. However, we think that with this last conclusion, the impact on try to use in the future in any existing machine is more considerable. Okay, thank you. Any question? Is there any question? Antonio, you don't have a question?
Sorry to disappoint.
No problem. Okay, then I think we can continue with the next presentation. Fabricio Silva is here. Martin, do you have the notes? Which one is the next presentation?
Yes, it's Fabricio. It's here.
Fabricio Silva.
I converted in host.
Multi-objective optimization.
I'm here. Hello?
Okay.
Hello?
Okay, Fabricio.
Okay.
Then Fabricio is the next presenter. And he's going to present a multi-objective optimization of the steering system and fuzzy logic control applied to a car-like robot.
See my screen?
Yes.
Okay. Good afternoon. My name is Fabricio, and I will present the student title Multi-Objective Optimization of Steering System and Fuzzy Logic Control applied to car like a robot. This work was developed in the laboratory of integrated systems from University of Campinas. Here are the topics of this presentation: the introduction, vehicle model, optimization problem, the results, and conclusions. There are many types of robots, but the wheeled robots can move with high speed and efficiency. Their structure is simpler and less expensive. They consist of fixed wheels and two wheels with active steering axis. The car. The car like a robot are suitable to many indoors and outdoor applications. Therefore, this work aims to define the steering system geometry. Therefore, this work aims to define the steering system geometry of a car like a robot. In vehicle model, initially, it's necessary to understand the turn behavior of a vehicle. At low speed, the tire slip can be disregarded, and its turning behavior is curbed by Archimedes geometry, in which all wheels revolve around the same point, as present in figure. The steering angles of the front wheels can be determined as a function of wheelbase, track, and curvature radius, as present in equation 1 and 2. At high speed, the lateral force and slip angle cannot be disregarded, and the lateral force should be associated with a tire model. In this work, the Passeca 87 tire model is used and present in equation 3. The vehicle steering system consists of a 4-bar mechanism, which is used to steer the vehicle wheels. In this study, the steering system geometry is defined in optimization. The length of bar 4 is constant. The length of bar 2 is defined in optimization. The distance between the intersection point of the first and third bars projection to the front axis is defined as a percentage of the wheelbase. This wheelbase percentage is defined in optimization. The first and third bars are symmetrical, and their lengths are determined as a function of a well-based percentage and the 2 and 4 bars length, as present in equation 4. With the steering system geometry defined in optimization, the system mass can be determined as present in equation 5. The position of steering system is performed using the position loop equation, as present in equation 6 and 7. The dynamics of vehicle steering system is obtained by applying the Lagrange equation motion. As present in equation 8. The fuzz logic control. To the vehicle steering system, a fuzz logic control was used. Therefore, the fuzz control defined the torque applied to the first of a 4-bar system based on the steering angle necessary to perform the maneuver. The input and output variable are defined by 3 membership functions described by Gaussian function. The Gaussian function defined by mean and standard deviation was present in equation 9. The presented equations and control are implemented in Simulink environment. The desired trajectory is defined by a dual maneuver. The error between the simulated and desired trajectory is calculated based on the correlation coefficient for the longitudinal and lateral direction, as present in equation 10. Optimization problem. The optimization problem was formulated with 3 objectives: to minimize the steering system torque required to perform the maneuver, to minimize the steering system mass, and minimize the trajectory error. The design variables are the second bar length, the well-based percentage, the mean and standard deviation of all Gaussian functions, and the Hurley rates. The optimization constraints is present in equation 15. The population is classified according to the fitness value, based on interactive adaptive weight genetic algorithm method. The trajectory minimization receives a double weight in fitness calculation to ensure that solutions with low drivability are avoided. The fitness is still present a penalty value, which assumes a value of 1 for non-dominated solutions, Pareto frontier, and a value of 0 for the other solutions. The results. The final population by the optimization is present in figure. The red stars represent the best compromised solution among the optimization criteria. This solution presents a low trajectory errors and mass. However, the torque for this solution is intermediate value when compared to the other solution. In this figure, is also present the simulation vehicle. The simulation trajectory of controlled vehicle is present in dashed red curve. and the desired trajectory is present in black continuous curve. It's possible to note that the two curves overlap in first half of the simulation, and the second they stay close. The optimization process determines 3 hurdles for the fuzzy controller present in this table, and the input and output membership function are present in this figure. In this work, the optimization process was able to determine the parameters of fuzzy logic control, the best solution obtained in optimization present a low trajectory error and mass, but for the steering torque presented an intermediate value. This happened due to the trajectory error having a greater importance in construction of the optimization algorithm. This work was supported by following organizations. I would like to thank all of them. LabSim, Unicamp, Petrobras, CAPES, and CNPq. Thank you.
Thank you, Fabricio. Any question? I have a question. Are you planning to build an experimental setup for this?
Yes. We still have a restriction to access the laboratory due to the pandemic, but in future, yes, we will implement the experimental.
Okay.
This prototype we have.
Okay. Marco, please go ahead.
Yes. Well, the work could be interesting from a mechanism point of view because, well, I guess you have got a nice, interesting experience on the steering mechanism. I don't understand why you put in the title robotics, because I don't see any robot feature in your work. I thought mobile robot with wheels and steering vehicles can be still considered robot, but in your work, I don't see any feature of robotic. Can you explain better? I'm asking why you indicate that this mechanism has an aspect for robots.
I understand your point, but the car like a robot, it's in literature considered a robot.
Sorry, but you not just because it's in a car is a robot. And well, this is the point. Your work is interesting and you got quite a good experience. It is also questionable how much novel you discover about this steering mechanism, but for sure has nothing to do with the robot. Okay, thank you.
Okay, thank you, Fabricio. And then we can continue with the next presentation. I believe Mauro Vaquero is present, right?
That's right.
We go ahead with the next presentation. Is Glauco Caurín. Okay, Professor Glauco Caurín. He's presenting in-hand manipulation via deep reinforcement learning for industrial robots.
Hello, everybody. I'm Glauco. Can you see my screen?
Yes, we see it. Perfect.
Yeah. Okay. I will present this work related to robot manipulation using deep reinforcement learning applied to industrial robots. We are at the University of São Paulo. And the idea here is that applications of robotic manipulation are still increasing due to more computational power and better theoretical approaches, especially those related to contact management and interaction control. Manipulation is still a challenge in many scenarios, especially when the rotation of the tool or part determines the success or failure of the task. In-hand manipulation techniques substitute or compete with regrasping, saving time during applications and unlocking different possibilities. In this very simple study, we conducted pivoting experiments in simulations, and the experiments consist in just reorienting a part around one rotation axis or rotation point without dropping the part. As you see here in the pictures, our motivations are we are interested in application involving in-place assembly, especially for aeronautic industry, where we don't have enough position, or we don't even need high position accuracy, and for robotic applications, point-to-point programming would make no sense. It would be too costing intensive for low number of parts. There's no repetition for the procedures, enough repetitions. We would also have custom shapes. Repetitive tasks include insulation, screwing, riveting for wing and empennage joining. In this figure here at the bottom left, you see what we are trying to replicate, what the humans do very easily. Thumb rotation in blue and the object in green and the target in red. Just as a reference, at the right side here, it will be the alternative approach with regrasping. That's not the focus in this work here, the paper we present. Just to mention, this is a side slide. Despite using just computer simulating this paper, we have different real scenarios. Here we are using some replication of mounting or assembling a aeronautic internal draw for the furniture draw that are used in the private jets cabins. Here in this work, we are exploiting these pivoting strategies. When we are working in collaboration, that the robot has contact with the environment, there would be two possible approaches. The first would be to model the whole environment. In this context, estimation of the stiffness or impedance, for example, of the contact between the robot and environment would be a challenge. It's non-linear, it's not constant. We are not doing this. What we are doing is a different approach, a second approach, just to adapt the robot behavior to the environment. We use cost function and change some parameters depending on initial guess. That's why we use reinforcement learning. However, this has also some drawbacks. Reinforcement learning is time consuming, and we cannot use just our experimental setup. We need to build a simulated environment. Okay, for the simulations, we use MuJoco. That makes this tool makes a very good job dealing with contact and friction. In our lab, we have collected good results using proximal policy optimization, a PPO, as a learning algorithm for dynamical system. our approach commands the desired robot behavior, providing reference values for the controllers. So we can test, this is in a higher level, so we can test it over different low-level controllers such as torque or position controllers. The state vector in our reinforcement learning implementation is composed by the angular error here is the first parameter. Second is grasping force, here is stated as distance, and two velocity terms. The drop here allows the agent to tell if it is actually holding the part or not. The action vector interferes in the gripper position and grasping force. The reward works with distinct rules. Experiments showed us that different behavior were required if the object is near the desired orientation or far away from it. This improved the stability using a variable error instead of a fixed value. For example, here just as a reference, 3 degrees force the agent to be more precise for smaller angles and allows it to be able to adapt for larger errors. Different agent architectures were tested, but it responded better for multi-layer perceptron with 3 hidden layers. The first hidden layer was 32 neurons, the second was 24, and the last hidden layer was 10 neurons. Training results showed better convergence with when we are using position control here in blue at this curve than when we use the torque controller at the lower controller levels. We implemented 2 different comparisons, just as I mentioned, one using the position controller in an industrial robot, and the second one using a torque control strategy. A second experiment explores the robustness of our approach dealing with different parts. 2 of them were not previously used or trained. Since the reward plotted in the previous slide here use a kind of average value, this can lead to some or hide some errors. The model may work very well for some range of angles and fail completely for other ranges. To analyze this, the figure at the left side here show the error in degrees when trying to reach a target angle. The shaded area represent some predefined success zones. This can be customized. For each target angle, 3 runs were simulated. And then we extract the mean values of each one. We implemented here the reinforcement learning. Let me see if I can run this video here to solve this in-hand problem and apply this to the industrial robot. Best results were obtained with the position controller. However, the model achieved a higher level of success for both position and torque. All tests with the trained part achieved small errors. Sorry for that. All tests with the trained part achieved small errors. When evaluated with different parts, the trained model was able to generate angles closer to the Nation 1 in range plus minus 20 degrees. Errors that were larger than the acceptable values were observed outside this range. In the future, we will increase the number of parts during training and maybe change some of the parameters also, and see how they have impact in the generalization. We will also planning to test the approach in our physical setup with the industrial robot, and of course we need to make use of some transfer learning techniques. Okay, that's it, and thank you for your attention.
Thank you, Professor, for your presentation. Is there any question? Okay. If we don't have questions, I think we are at the end of the session. Martin?
Yes, there are no more works. Then
okay. We have a break right now.
We have a break for the general attendance and the members of the International Scientific Committee. We have a meeting in another link, not through this platform. So I will put here the title of the next presentation somewhere of the were canceled. So keep informed. So in an hour, yes, 1:30. We will come back 1:30.
Okay, see you then.
Thank you, everybody. Thank you, Rogelio, for chairing this session.
You're welcome.
See you, Marco. Thank you, Glauco. Nice presentation.
Thank you, for the organization.
Presented by Mariana. And the last one will be presented by Mohamed. So I will be the first speaker. I will share my screen. Yeah. Martin, can I ask you a short question?
Yes.
Can we open the papers for discussion one by one or at the end of the 3 presentations?
When you want it. You can interrupt your presentation.
I suggest that we can, okay, but one by one should be better, I guess. I'm not sure if you are seeing.
Not yet. In full screen.
Okay. Sharing. Are you seeing?
Yes. Perfect.
Okay. So my talk of today is about the modeling and simulation process of frictional contacts in multi-body dynamics. So the focus will be on the contact detection and the way how we can solve the contact problems, of course, in the context of dynamics of rigid body systems. This is the outline of my presentation. I will show some motivation for doing this work, some general issues related to contact frictional problems. Then I go for the multi-body dynamics formulation, and then I will present the fundamental ingredients that we need when we are interested to model contact problems, namely the geometry of contact, the resolution of contact, and I will, after that, present some examples of application, and I will end my talk with some concluding remarks. So in terms of introduction, I would like to say that it is important to mention that contact problems deals with the deformation of solids when they contact with each other at one or more points. And of course, frictional contact mechanics is the same problem, but when we include the frictional effects. In turn, a multibody system or a mechanical system can be defined as a collection of links or bodies which can move relative to one another. In terms of multibody dynamics, when we can understood this discipline as the study of systems with multiple bodies whose interactions are affected by the application of external forces and moments, and of course the presence of kinematic constraints. In a similar way as it was presented in the keynote of today by Manfred. So the key idea when we are interested in to formulate contact problems in dynamics of mechanical systems is, first of all, we have some geometry of the contact interaction. In this simple case, we have a radius, we have some indentation, or sometimes called pseudo penetration or virtual penetration. And the result of this interaction, we have some normal and tangential forces. And typically these normal and tangential forces are modeled as spring and damper elements, but in normal and tangential directions. So basically we have some geometry of the contacting surfaces, we have contact interaction, and the result of this interaction basically are normal and tangential forces. So this is the key idea when we are modeling multi-body systems with contact events. In terms of keywords that have been inspired my developments and in my group is of course the work by Newton, not only the equations of motions, but also Newton's impact law, and of course Coulomb's friction law, the work by Henry Hertz in terms of normal contact force, and more recently the work by Anton Krossel is a seminal work that is a classical work in multibody dynamics, and more recently the work presented by Lankaran and Nikravesh, and also in a different way that I will present later, the developments presented by Professor Pfeiffer and Professor Glocker. So this is the key references that support the developments that we have presented and proposed over the last 20 years. So in a simple way, we can say that contact impact events can be presented in many mechanical systems, if not in all of them. And of course, in some cases, the response of the systems depends on the contact interaction. So we have developed over the last years some computational models for dynamic modeling and analysis of contact impact events in the context of multibody systems. In a simple way, the three main factors when modeling contact impact events are the geometry of the contacting surfaces, that can be simpler or more complex, the local and the material properties, and of course the constitutive law or the approach that we use to represent the interaction between the contacting bodies. Here we can see one example of application, which is a walking machine. If I remember well, this was our first model that we have done in our group many years ago. And of course, we can see some interaction between the feet and the ground, the horizontal plane, and also in the stairs. So we can see an application whose contact interaction are crucial for the success of the modeling of this walking machine. Another classical problem is this woodpecker toy, which is a benchmark in the context of multibody dynamics with contact. We have some experiments and also some computational simulations where we used two different formulations that I will discuss later. Now I'm moved to discuss some general issues related to contact events. So basically we have some important characteristics in terms of duration of contact, which is very short. And as a consequence of contact, we have high force levels. And of course, we have some dissipation of energy. We can have, in some cases, continuous contact. That means that the contact process is finite. And also we can have contact that is immediately followed by rebound. In general, we call this situation impact. As we can see in this animation, we have some periods where we have a permanent contact between this journal and bearing. And in some cases, we have free fly motion, no contact. And in other cases, we have impact, which is immediately followed by rebound. Very important in terms of simulation is the resolution of contact itself. And one crucial issue is the transition between the different contact regimes. Basically, we have contact and non-contact situations. And then when we have a friction, we have to pay attention how to deal with this transition between sliding and non-sliding and sticking of the contacting bodies, as we can see in these two animations that are for normal and tangential contact phenomena. In terms of contact points, in a general way, we should start with the definition of the contacting surfaces and also the establishment of a methodology for the contact detection of the potential contact points. Of course, we can have simple geometries as this woodpecker toy, and we can have a complex scenarios as this car accident. In terms of resolution, we can have two different approaches that we have using in our group. We have regularized or penalty approaches, and we have the non-smooth models, typically in terms of LCP formulations. These are two different ways how to formulate and to solve contact problems. So basically, in the regularized approaches, we can assume or consider that the bodies can locally deform, and this deformation will be used to evaluate, to compute the contact forces. In our opposite sense, when we are using non-smooth models, the bodies or the surfaces are assumed to be entirely rigid, which means that we have no deformation. In this slide, we have a short comparison between these two different approaches. The regularized models, as I said, the bodies can deform. We use this penetration to compute the contact forces. In some cases, due to the stiffness, the systems can exhibit some high frequencies. When dealing with the dynamic analysis, we in general require more time steps in terms of time steps with smaller size. And then also we have some difficulties in terms of identifying some properties. When we use non-smooth models, as I said, the bodies are rigid, the impenetrability condition is considered. We applied moment and impulses. In terms of computational, this approach is robust and quite stable. We can use larger time steps. So this is the basic characteristics that can be discussed with detail in terms of examples of applications and to show the advantage or advantages of each simulation. And of course, we cannot say that one is better than another. It depends basically on the discretization of the system and also on the mechanical system to be analyzed. In terms of multi-body systems, basically we have a collection of bodies with kinematic joints and actuated by forces and moments, and then we have some motion produced. This is the way how we formulate the equations of motion. Typically, we use Cartesian coordinates and generalized coordinates. This is the way how we assemble and solve the equations of motions when integrating in a computational code. One critical aspect when dealing with contact problems is the definition of the precise instant of contact and the transition between these two states. As we can see in this animation, two different time steps produce different results. So we should pay attention, and in some cases we need to adjust the time step just before we suspect that the contact will start. So the basic idea of this slide is that we need to reduce the time step when the contacts are approaching to each other, and after the contact we can increase the time step in order to have a better computational efficiency. In terms of geometry of contact, in a simple way, we have surfaces or bodies that are represented by a collection of points that have some spatial position, sense of orientation, and the measure of proximity, which is basically a distance between bodies. As we can see in these three figures, we have non-contact situation, the beginning of the contact, and the contact where the pseudo-penetration delta is less than 0. We can have simple geometries, like in a bouncing ball example. We can have complex geometries, like in a planar knee articulation, and we can have even more complex scenarios if you consider a three-dimensional knee articulation. For this particular case, we can easily define an analytical expression to check if the bodies are in contact or not. In a similar way, we can apply the same approach, for instance, for planar revolute clearance joints. When we have complex profiles, we should impose some conditions in terms of direction of contact. And of course, we can use the same methodology and extend it for three-dimensional problems. As we can see in these three-dimensional surfaces that define the condyles and the plateau tibial of the tibial bone. In terms of the resolution of contact, one of the most well-known approaches is the formulation presented by Anton Crossley. Basically, we have this conservative or elastic and dissipative term. This is the representation if we plot the penetration or indentation against the contact forces. As we can see in this plot, we have some amount of energy that is dissipated during the impact. And over the last 30 years, different models have been proposed which represent some progresses, and in some cases we have similar results. I'm going to show quickly some of these models, and basically the difference is the amount of energy that we can associate with the area of this loop in this plot. So We have basically 20 or something models. Some of them are not included in this presentation. In terms of friction, we can say that we have also different regularized approaches, which have been proposed basically to overcome these difficulties associated with the classical Coulomb friction law. I also will show some graphical effects and the properties associated with each model. We have the original Coulomb model, here well defined. Coulomb with friction, the model proposed to accommodate the Strebeck effect, the solution proposed by Carnop, Trelfall, which is very efficient. Bingiso and Akai is also very popular in terms of simulation of frictional impacts in mechanical systems. Ambrosio also proposed an approach to avoid the problems of Coulomb's friction law. Basically, we have different solutions. These ones are static. There are also some dynamic models. Now I'm going to present some examples of applications where the contact have been modeled with different approaches. This is a benchmark problem in contact examples when dealing with non-smooth and regularized analysis of contact events. So here we have some phase portraits for the woodpecker, which can show that the motion is periodic with different phases, and the period of this motion is around 0.1146 seconds. We obtain these results for both regularized and non-smooth approaches. Here we have a sequence animation and a video of the model. If we pay attention, we can see the different scenarios of contact. In this particular case, we have 3 potential contact points. We can see that we have a sleeve or a clearance joint between the road and the feet of the woodpecker. This animation was performed with regularized formulation. And also we have some experiments that allowed us to compare and, let's say, validate the approaches. Another example of application is an industrial application, which is basically a cutting file machine, which is relatively robust and demanding from frequency operating conditions, but from mechanical point of view is not complex. Basically, we have a cam follower mechanism, but we have a very small stroke for a very high frequency. So this very small stroke affects the quality of the file. Here we have an animation sequence when the command follow lost the contact until the contact is reestablished. And this time interval is quite important for the quality of the file. Here we can identify the follower velocity, and the impacts are, the first impacts are followed by rebounds, and after that we have continuous or permanent contact. I guess here we have an animation. Here we can see, okay, all the system, the cutting file, and of course the mechanical system, the command follower. So to conclude my talk, the idea of this presentation was to show the importance of contact modeling and analysis in the context of dynamics of mechanical systems. The 3 main issues are the definition of the contact points, the evaluation of the contact impact forces, and of course we should pay attention of the transition between different regimes, non-contact, sliding, stitching, and the reverse sliding. We can say that the contact dynamics is a very complex and in some cases complicated problem that still requires some research to reach better models and solutions. So for future development, I think that new algorithms still need to be proposed, namely for this transition between different contact regimes, also benchmarks to get some physical response to validate some numerical and computational approaches. And this is the key idea of my talk. Some acknowledgements to institutes that have supported our research. And this was basically my talk. So now the presentation is open for discussion. If you have some questions or comments. Since one presentation is missing, we still have some time for questions or presentations. So Martin.
I have just a little question. In a general way, the multibody can approach one each other, like in the video games and motor graphics, that can detect all the impacts very fast and quickly. Which is the geometrical problem to identify, for instance, which body will be entering in contact with the other? Is it a from computational geometry problem, or you can afford it from another way, like ray tracing or another algorithms? Which are you using, for instance, for the knee? Which algorithm for computing the projection only of the surfaces?
In our case, most of our problems, we do not have many multiple contacts. So typically we define the geometries as surfaces, collection of points, and or in some cases we have some analytical expressions, and then we check for the minimum distance between the potential contact points, and among them then we select the point with the smaller distance between the contacting surfaces. So basically we consider that we have a single contact point in order to apply over it the contact forces. In this case, we are not very worried in terms of real-time simulation as in video games is a different issue. Another alternative that we have less experience is to solve functions to find zero. If the distance or the gap distance is a function, we can use some numerical tools and try to find the zero of the functions. But most of the cases we have free surfaces, like in railway contacts, and also we can have some lookup tables approach. But basically we are looking for the potential contact points, and among them we'll look for the minimum distance between contact points.
So you know him a priori?
We don't know him a priori, but we can say that we can estimate in which zone is the potential contact zone exactly.
Okay. And from the time integration challenge, you are using penalty factor to set depending on the problem. Do you design some automatic?
Yes, exactly.
Setting of the factor.
For the case of regularized formulation,
yes,
we can adjust the time step just before the impact. Okay, we suspect that we are faced with the first impact, we can reduce time step. When we are using non-smooth formulations, this is not so critical. We can use larger time steps, at least according with our experience and the literature we are consider. The time step when using non-smooth formulation is not so critical because we do not use the indentation itself.
Thank you.
Any other questions or comments or suggestions? Are we late, Martin?
You're okay.
Perfect.
So you can continue with Mariana.
Yes, if we have not more questions, we can move to the next presentation that will be done by Miss Mariana. Mariana, are you ready?
Yes, I am. Can I share my screen?
I think so.
Okay, can you please confirm that you're seeing my screen?
Perfect.
Okay. Good afternoon, everyone. My name is Mariana Rodrigues da Silva, and the work I am presenting you today is entitled Modeling Spherical Joints in Multibody Systems. This work has been developed at the University of Minho in close collaboration with Institut Superior Técnico from Portugal. In the beginning of this presentation, I will introduce the theme of this work, and then we will move on to an explanation of the kinematic and dynamic aspects of spherical joints. A demonstrative example of application will be considered, and I will finish this presentation with the concluding remarks regarding this work. Spherical joints can be utilized in many applications. On one hand, these types of joints can be found in many machines and mechanisms, such as the case of a car suspension in automotive applications. On the other hand, these types of joints can also be used in the anatomical domain to model some articulations of the human body, such as the case of the hip joint. These are just two examples where we can use spherical joint modeling. However, there are many more. So, bearing all this in mind, we can acknowledge that spherical joint modeling is an area of investigation very worth studying. In spherical joints, a spherical part of one component, which is the ball, resides inside a spherical part of the connected component, the socket. Bearing in mind the type of applications in which they are designed to operate, spherical joints can be characterized using different types of models. In this work, we used 5 models: the ideal joint, the clearance joint with and without friction, the lubricated joint, and the bushing joint. Therefore, the aim of this study is to analyze and compare the influence of these 5 spherical joint models on the dynamic response of mechanical multibody systems. To analyze these 5 spherical joint models, we must first understand their kinematic aspects. The simplest case is to consider the spherical joint as an ideal joint, which means that there is no clearance between the ball and the socket. Ideal spherical joints allow 3 relative rotations between the bodies connected and constrain the 3 relative translations. The kinematic constraint equation used to model an ideal spherical joint is this one, and essentially it means that point Pi on body I must be coincident with point Pj on body J. Taking the first time derivative of this constraint equation, and after some mathematical manipulation, we can obtain the Jacobian. In a similar manner, taking the first time derivative of the velocity constraint equations, we can obtain the right-hand side of the acceleration equations for an ideal spherical joint. Another case is to consider the spherical joint as a clearance joint. In multibody systems, instead of dealing with kinematic constraints, as in the case of the ideal joint, a spherical clearance joint deals with force constraints. This means that the bodies are freely available to move in relation to one another, and a spherical clearance joint does not constrain any degree of freedom from the system. The difference in radii between the ball and the socket is defined as the radial clearance. In addition, the vector connecting point Pi to point Pj, as we can see in the figure, is defined as the eccentricity vector. Please now be aware that I will change the image of the clearance joint to show you the penetration that occurs when there is contact between the ball and the socket in the tri-spherical clearance joint. One of the most common solutions utilized to avoid or reduce the contact between the ball and the socket, or to minimize the energy dissipation, is to add a lubricant in the space between the ball and the socket, which is the clearance space. The high pressures that develop on this fluid act to keep the ball and the socket apart, which prevents the contact between these two components. Dynamically loaded spherical clearance joints with lubrication can be classified into two main groups: the squeeze film action and the wedge film action. The squeeze film action is dominant when the relative rotational velocity between the ball and the socket is small when compared to the relative radial velocity. And the contrary is true for the case of the wedge film action. In other applications, the use of bushing elements might be an interesting option. Bushing elements are composed of elastomeric material, and they can be used, for example, to handle misalignments, reduce shocks, or reduce vibrations. A very important aspect to take into consideration is that the kinematic aspects of spherical clearance joints with lubrication and with bushing elements are similar to those of the dry spherical clearance joint. And this means that in these two cases, we also do not consider kinematic constraints, but instead we consider force constraints. We have studied the kinematic aspects of spherical joints, and we have acknowledged that we will need force constraints in some of the spherical joint models we want to use. So we have to study the dynamics of spherical joints and choose the force model for each of the spherical joint models. Starting with the dry clearance joint. In this work, we chose to use the Lankarani and Nikravesh contact force model. And when we wanted to introduce friction in the system, we used the threefold friction force model. For the lubricated joint, we used the Pinkush and Sternlich lubrication force model, which is based on the squeeze film action. We chose this model because in the demonstrative example of application that we'll be discussing later, the squeeze film action is the dominant one. And finally, for the bushing joint, we chose to use an approach proposed by Ambrosio and Verissimo in 2009, which is based on the bushing deformation. We are now ready to move on to the demonstrative example of application. In this work, we considered a spatial 4-bar mechanism. This mechanism is composed by 4 rigid bodies: a ground, a crank, a coupler, and a rocker. These 4 rigid bodies are connected to each other using 4 joints: a revolute joint between the ground and the crank, another revolute joint between the ground and the rocker, a spherical joint between the crank and the coupler, and finally another spherical joint between the coupler and the rocker. In this work, we chose the spherical joint connecting the coupler to the rocker to introduce clearance and bushing. All the other joints were considered to be ideal, so we used kinematic constraints. It is also important to note that the configuration of the system that we see here in this figure was taken to be the initial configuration. Moving on to the results we obtained. We studied the Z components of the position, velocity, and acceleration of the rocker. From these images, we can see that the frictionless joint model, which is highlighted in green, exhibits more oscillations and produces significantly higher velocities and accelerations when compared to the other models. This means that the response of the spatial 4-bar mechanism with a dry clearance joint without friction becomes chaotic. In fact, as we can see from the blue curves, the addition of friction tends to smooth the behavior of the system, making it less chaotic. We can also observe that the response of the spatial 4-bar mechanism with the ideal joint model produces significantly lower accelerations when compared to the other models. For the lubricated joint, which is highlighted in red, we can see that the results produced by this model tend to be close to the ideal joint case. And this is true because the lubricant acts as a filter by reducing the levels of the peaks that are caused by severe dry impacts. And finally, as expected, the bushing joint model is the one producing results closest to the ideal joint case. This means that the bushing joint model stabilizes the system, making it less chaotic. We also studied the mechanical energy of the system. As we can see, the dry clearance joint model with friction is the one dissipating the highest amount of energy. And this model is followed by the frictionless joint and the lubricated joint models. The bushing joint is the one dissipating the least amount of energy. As we can see from observing all these four figures, the model that produces results that differ the most when compared to the others is the dry clearance joint model with friction. And that's the reason why in this animation, I am showing you a comparison of the movement of the mechanism with the ideal joint case and the dry clearance joint model with friction for a simulation time of 2 seconds. Moving on to the concluding remarks of this work. The dynamic modeling and analysis of spatial mechanisms with different spherical joint models has been presented in this work. The main kinematic and dynamic aspects related to these models were described under the framework of multibody systems methodologies. A spatial 4-bar mechanism was considered as a demonstrative example of application. And finally, we can conclude that overall, the spherical joint models strongly affect the dynamic performance of the system, and this is essentially visible in terms of accelerations and mechanical energy of the system. Thank you very much for your attention. I am now available for any questions or comments you might have. Thank you.
Thank you, Marianne, for using precisely the 12 minutes schedule. The paper is now open for discussion. Questions or comments, please. Any specific comment or question from the audience? If not, Maria, I have a curiosity, a simple question. Can you please comment or say a few words about the computational efficiency, the computational effort of these different approaches, ideal joint, clearance joint with friction, without friction, bushing and lubrication?
Yes, concerning the computational efficiency, we studied and we saw that the ideal joint case was the one producing faster results, which have better computational efficiency. And then I think we have seen that the friction joint case was the one having higher computational, the frictionless having the higher computational or the higher computational cost.
Okay. And in terms of the simulation of with the lubrication and with bushing elements, are those approaches, let's say, relatively efficient, or they need a lot of effort, a lot of computations?
when compared to the ideal joint case, they need a lot of effort. But when compared to the frictional joint model, the results are not so different.
Okay, thank you. Any other questions?
Yeah,
Go ahead, Mario.
Hello, Mariana and Paulo. Thank you. Very general questions. It is just to grasp the whole idea. The first one is that, as I saw in the slide 12, the self-rotation about the axis of the coupler is free, isn't it?
Slide number?
Slide number 12.
12.
And let me see if I can.
Sorry about these general questions.
No problem.
Which was the number of the slide?
12.
12.
The 12 is this one.
No, 12.
This is 11, 10.
Oh, 12 is the...
Okay, don't worry. Maybe 14. It's okay. I mean, in your model, the coupler, the connecting rod, there you have to in both extremes you have spherical joints. Yes. So is this connecting rod free to roll or to spin about its axis?
No, it's not.
Mariana, can you show the slide with the kinematic configuration of the for-bar mechanism? Yes, this one.
Yeah. So the coupler is completely. Is there a free degree of freedom there or not? I am just asking that.
In here, there is a free degree of freedom. In here, when we introduce friction clearance.
Okay. So it's controlled by force. Okay, exactly. I get it. So sorry about that. And another question is that talking about the integration scheme. I mean, to take into account this lubricant and also the bushing, does it affect greatly the step size of the integration scheme, or what kind of integration scheme you are using there?
Here we used MATLAB for using OVA15S, so it changes the time step when
automatically.
Yes, exactly. When he thinks he is approaching contact, he uses a smaller time step.
Okay. So it is controlled by the algorithm by itself.
Exactly.
Okay. So, it's very interesting. Congratulations about the work. It's very interesting. So that's all for me. Thank you very much.
Thank you.
Thank you, Mari, so much for your comments and questions. Any other short comment or quick question? If not, I say thank you, Mariana, for your presentation, and I will move to the last presentation of this session. That will be done by Mohamed from Harbin Institute of Technology. Mohamed, are you ready to share your screen with us?
Yes, sir.
Perfect.
Yes, sir. Can I share my screen now?
I think so. Please go ahead. Good to see you. And please.
Is it clear for everyone?
I think so. So the floor is yours. Go ahead.
Okay, my presentation talk is number 43. And I am very proud to present my talk in the 7th International Symposium of Multibody Systems and Mechatronics. My talk will be about a multibody dynamics modeling of Delta robot with experimental validation. The abstract of my work will be a multibody system approach used to study the kinematics and the dynamics of Delta robots. This systematic approach is developed based on the load assumption due to the end effector movements. The multibody model is constructed using MATLAB symbolic toolbox. The system of study type is D3S800 Delta Robot System, which is utilized to study and validate the multibody model. A comparison of the experimental data and the numerical solution is also investigated. In figure 1, we can see the graphical abstract of my work. First, we have an actual delta system. We set an initial motion to the end effector to move in space. Based on the motion of the end effector, we can measure the three rotational motion of three revolute joints of motors. The actual measurements of motor rotations can be compared with the simulated multi-body system model data. After comparison, we can validate the model and verify our model. Here, the system mainly is 3 degrees of freedom. The end effector can achieve 3 translational motions along X, Y, and Z axes. Another degree of freedom, which is rotational motion of the end effector about the Z axis. But for simplicity, we consider only in this study the 3 translational motions. Delta robot consists of 3 identical chains. Every chain consists of number of joints and bodies identically equivalent to the other 2 chains. For example, one chain consists of 1 revolute joint, 4 spherical joints, and 4 revolute joints. The first revolute joint connecting directly the active arm to the electrical motor, and the arm is connected with 2 forearms in 4 spherical joints. The 2 forearms connected together by upper rod and lower rod by means of another 4 revolute joints. The dynamic characteristics of our model performed using the inertia only of the system. We does not apply any external forces. We depend on the measurements of masses of the bodies measured from the actual system. Here are the all bodies consisting the whole system of Delta robot. We have 1 fixed base in blue color and 3 active arms in brown color, arm 1, arm 2, and arm 3, and 6 forearms connecting each arm to the end effector. We have 6 rods, 3 upper rods and 3 lower rods, and we have only 1 end effector. In table number 2 is the joint of 1 chain written in order. Here is the multibody model of 1 chain. The general formula of a multibody formulation of 1 chain will be the same for the other 2 chains. We denoted the revolute joint by AI. AI is a notation of a revolute joint. AI may be A1 and A2 and A3 for the other revolute joints. The spherical joints denoted as BI1 and BI2 for the upper spherical joint, and CI1, CI2 for the lower spherical joints. The revolute joint between the 2 forearms and the 2 rods denoted as S and T. We can reach a point on the end effector by either 2 ways, by defining the point with respect to the local frame of the end effector, or by defining this point with respect to the global frame of the whole system. The global frame attached to the fixed base in a plane containing the 3 AI points together. Again, I may equal 1, 2, and 3 for chain 1 and chain 2 and chain 3. Here is a model of fixed joint between the fixed base and the ground. The multibody model of the fixed joint is a constraint vector equation. The first part here is the translational part, which prevents the fixed joint to make any translation. And the other 4 parts in Euler parameters prevent the fixed joint to make any rotation about any axis. All these constraint equations should equal to 0 to prevent any motion of the fixed ground joint with the base. Here is the model of the revolute joint. For example, between arm1 and fixed base, the first 3 terms prevent the revolute joint to make any translation. The revolute joint only allowed to make a rotation motion about an axis passes through the joint axis here. Also, an example for the model of a spherical joint, it's CI1, for example. It consists only of 3 equations because the spherical joint is allowed to make rotations about the 3 axes. The other spherical and revolute joints can be modeled similarly to revolute joints and the spherical joints indicated in figure 5 and figure 6. Here is the general formula of the equation of motion of the system expressed in multi-body system dynamics. The first term here is the mass matrix, and CQ is the Jacobian matrix. The Jacobian matrix is the partial derivative of constraint vector of all the system with respect to the all coordinates of the system. CQT is the transpose of Jacobian matrix. Q double dot is the second derivative of coordinates of the system. Lambda is the Lagrange multipliers. Q is the vector of external forces, and in our example, it equals to 0 because we don't have any external forces applied to the system. QD is a quadratic force vector, and it may have some values because of the inertia of the system. By solving the equation of motion, we can solve for Q double dot and solve for lambda. Q double dot can be integrated to determine the coordinates and the velocities for the system bodies. The Lagrange multiplier vector lambda can be used to determine the generalized reaction forces used to establishing the design process. So we can solve this equation for Q double dot and lambda and the first derivative of Q dot and Q. Here is the operation of the actual system. We have control unit. By using this control unit, we can manage the motion of the end effector. Based on this motion, the motors will give the rotational motion to the arm. We can see also encoders directly attached to the motors. These encoders transmit the signal of velocities to the controller of the system. A PC can be connected to the controller to display the signals of the motors. The motion criteria of the end effector tested was 100 millimeter per second velocity in a planar motion XY. The end effector will move in a plane XY, but in degree 45 between the 2 axes. We can see the end effector elevated at distance negative 847 millimeters because we have the positive Z direction pointing upward. So the end effector is located in negative direction. We made a simulation performed using MATLAB and determined the solver of MATLAB as Adams ODE 113. We run the numerical integrator for 5 seconds for the prescribed motion criteria. By solving the dynamic equation aforementioned, the system accelerations obtained and integrated forward, the system bodies, velocities, and configurations are computed. Here is the reaction forces acting on the base frame due to the masses of the system. And here are the torques needed from the 3 motors to drive the system under its inertia. Here is a semi-scape model. First, we modeled the motion of the end effector as linear motion with the specified velocity to obtain the simulated rotational velocities of the revolute joints. The second step, we fed this rotational velocities to the revolute joints to determine the torque and force. Because the revolute joint should determine first the input to be provided by input to compute the torque and forces and etc. The comparison between multiple system and experimental data shows a very identical curve because the system has a controller unit which modifies and the system is compatible, which generates a very identical curve to the multi-body system model. Also, the dynamics, we compared the dynamics of the model by the semi-scape model because the system does not have force sensors. We depend only on the simulation to compare the dynamics of the model. Here is the constraint evaluation of a revolute joint. We can see that the violation of constraint does not exceed 10 to the power 13, which means the computational efficiency of the multibody system model. The conclusion of my work is a symbolic multibody system formula, which describes the system is carried out and the explicit equations of motions of delta robot have been derived. The solution of the equations of motions involves the system coordinates and associated Lagrange multipliers as well. The paper describes an experimental test rig of D3S800 delta robot system in front of end effector movement, and the measured motors velocities are collected and compared with multibody model. The comparison shows a very good agreement with the which encourages the enhancement of the model by examining unconventional operating conditions. Lagrange multipliers can be used to estimate the generalized reaction forces, which can be utilized in the optimization of delta robot design. In going and future work, multibody model will be used for parameter identification and design optimization of delta robot. Finally, this work was supported by National Natural Science Foundation of China, and I was Mohammed Al-Shami. I am Assistant Lecturer of Mechanical Engineering at Penn University. Thank you for watching.
Thank you, Mohammed, for your nice presentation and also for using your 12 minutes.
Thank you.
So we have time for some questions or comments before going to the coffee break.
Okay.
We have time for a simple or a short question from the audience. If not, I have a curiosity. You are showing an interesting work that combines both numerical approach and some experiments. But in terms of computation, you are performing a very long simulation. 5 seconds is relatively long. Did you consider some numerical stabilizers in terms of the control or elimination of the constraints violation, like Baumgart or another technique?
I think the stabilizer is integrated in the SimScape tool itself, because I modeled here. Let me show you my model. Here is the model. I modeled it in SimScape. Each chain here modeled as itself, and by clicking run, I think the SimScape tool has a stabilizing technique for this problem.
Can you please comment what type of stabilizer, Baumgart style or penalty approach? Because you showed the general formulation of the equations of motions in one of the slides that are basically solved for accelerations. And if we do not pay attention to the violation of constraints, we can have the progressive growing of the violation of constraints. And as I said, 5 seconds can be a very long simulation in terms of multibody dynamics.
But I said in 5 seconds. 5 seconds is not very long, because the system is this system. This is a parallel system. Parallel systems can achieve high speed with high stiffness. So this advantage, but so this is the advantage of parallel system. So we chose the delta robot because it has a moderate complexity, and at the same time it can achieve higher speeds without constraint violation.
Anyway, I can suggest you to pay attention to this issue. You mentioned a reference that describes different approaches to control the violation of constraints. So I congratulate you for your work. Nice presentation also. So
thank you.
To conclude and to close this session, I would like to thank all the presenters, Marianne and Mohammed mainly, and I also would like to say some words to say thank you to the organizers for this tremendous effort to have this online conference. Of course, we prefer to be in Argentina and to have some local experience, you know. So thank you so much, and I think now we can have a short break. Am I right, Martin?
Yes, thank you very much, Paulo, for chairing this session. Yes, we
My
will do
pleasure.
just 10 minutes pause break in order to not shift too late. Is yes, 14:50. 10 to 3. So we will shift the presentation only 10 minutes, all the following presentations.
Okay, perfect. Thank you so much. See you.
2:50 or 14:50, we will coming back.
Perfect.
Martin Bloedorn is here. We will try to organize the speakers. Martin? Yes.
Martin, did you change the blocks? I mean, you switched the blocks?
Just no, just
No, it's just a question.
no, let me show you.
Okay, don't worry.
Just a delay of 10 minutes. Giuseppe is here. Giuseppe Carbone will be the chair.
Hi, Giuseppe, how are you?
I'm fine, thanks.
You look
Here
great.
is afternoon. How is there? I guess you're in Portugal or somewhere else.
I'm in Portugal.
All right, good. So we have the same time.
I think 1 hour difference.
Okay. Yeah, here it's the 7:40 p.m.
It's 1 hour less here.
All right. Good. Okay, we will meet in a few minutes for the next session then.
Perfect. See you.
10 minutes.
Great. See you later.
See you, Giuseppe. I will be contacting the presenters.
Perfect.
Martin Bloedorn.
Can you hear me, Martin?
No, Martin. Just
all right.
Raise the volume.
Now, perhaps?
Yes, perfect. Martin.
Oh, now I don't. The cool thing is now you hear me, but I don't hear you. Let's.
Okay.
Wait.
Martin is ready. Oswaldo Rivera.
Let me do the other thing.
Oswaldo Rivera is here. Let me go to just to configuration, just to Sean is here. Sean Rodriguez Torres. We can test the sound unless. So Martin, check. Magalis Ganga.
Here, how are you?
Hi, Magali.
Good
Can you guys hear
afternoon.
me now?
Good afternoon.
Just really low.
Oh,
who's
fantastic.
talking? Martin.
Of course.
Martin
I mean, it
talking.
can never really work completely out of the box. That would have been too easy, right?
We wouldn't have jobs, right?
Did it get any better? Because I'm pushing the volume the hardest as it gets. Okay,
Yes,
it improved.
now we hear you very well.
Oh, okay, then that's great. All right.
So Martin here, Oswaldo Rivera. Oswaldo, I know him. I see him, but
All right, and I cannot.
are you ready, Oswaldo? No. Sean Rodriguez.
I suppose.
And Giuseppe is ready. Okay. So the people of Colombia is not responding, but they should be here. I can see them.
Suppose my screen is also up at this point.
Yes, if you.
Mike, Like
If
I
the
have used
parent,
Zoom twice. My company is super old-fashioned. They love old Skype, so Zoom is a bit alien for me. So if y'all are seeing stuff, it's all
it is
good.
nice.
All right.
But Fidasol, I will introduce firstly to Giuseppe Carbone as a chair. So, Martin, please, up to now, stop cheating. And then after presenting Giuseppe, you will start. Okay?
Super. All right.
It works. It worked very well. I can see it.
All right.
Oswaldo is here.
Hi, I'm here. Yes, sorry.
Hi, Oswaldo. Are you ready?
Can I have more, like 2 minutes more, please?
Yeah, you are after Martin. Martin will take 15 minutes.
Yes.
Okay. So I go after this presentation, right?
Yes. And
Sure, sure.
Sean, your partner, Sean Rodriguez.
I don't see him, but I'm going to take him right now. Okay.
I am seeing here. Let me check. Hello?
Actually, I'm looking at the camera like this.
Hey. Hey,
Hi,
Martin.
Sean.
Sorry. I'm ready in 30 minutes, no? Isn't it?
Yes, you are
Okay.
after your friend Osvaldo.
Yes,
You're from
I'm
the same group,
ready.
I know, as I know.
Yeah.
Okay,
Okay.
thank you.
No, you're welcome.
In 2 minutes, we will start.
All right. Also, I think Danielle contacted you, Martin, to change the time of my presentation. I appreciate you managing it because with the time difference, it would have been hard with the original time. I think the original time was like 1 p.m. or something. So thanks for managing that.
Daniel?
Daniel Ponce.
Daniel Ponce?
Yeah.
Yes. I couldn't understand what you're saying recently.
No, it's just that my original presentation time was, I think, 1 p.m. and I think he contacted you to change it. So
Yes, we changed it.
I appreciate that
Yes.
that you guys did it.
Okay.
Because otherwise I would
You're
not have
welcome.
made it. Yeah.
Yeah, we changed it by Giuseppe presentation.
No.
So we can start. I will start introducing Professor Giuseppe Carbone from the University of Calabria, Italy. He's the chair of the technical committee for the robotic and mechatronics from the IFToMM. Now he will chair the Mechatronic system for assistive technology and rehabilitation. Please, Giuseppe.
Thank you very much, Martin, for this kind introduction. Welcome everybody to this session. And I will introduce the first speaker, and I will remind you we have slots of 15 minutes each. So I warmly recommend you to keep the time schedule. So 12 minutes presentation plus 3 minutes question and answers. First speaker is Martin Bloydon, and his paper is on Curvatio, low-cost measurement system for spinal curvature. So Martin, the floor is yours.
Thank you, Giuseppe. Well, first of all, thanks everybody for being here, for the time. It's going to be a little compressed on time, but I'll try to make it in the 12 minutes as suggested. If at any point I'm talking too fast or the audio is bad, usual virtual stuff, just let me know. So the work, as mentioned, is called Curvatio, a low-cost measurement system for spinal curvature. And just a little overview on how this presentation is going to happen. I'm going to briefly show you guys a video on what the project is about. And the idea is just to give a big picture, because I think it then makes it easier later during the presentation to connect the little bits and pieces together with the whole context. I think it's easier to follow in that case. After the little trailer, I'm going to sort of start from the actual beginning and present what was the motivation for the project. Then go into the details of design and implementation, how we validated our prototype, and then close off with a few thoughts and comments. Right. So as I mentioned, the first thing is just a little trailer. So what is Curvatio? Curvatio is a little device. You see here our prototype that you connect via USB to your computer. And that allows you to essentially, in real time, make a measurement or an assessment of a patient's spinal curvature in both the sagittal and the coronal planes, so front and side, essentially. Once you have collected the measurement, which you see in real time, you can actually extract information out of this measurement. And within the same software tool and within this, using the same device, you can also make goniometer measurements, so angular measurements and range of motion measurements. So this is just for really quick overview on what the project is. And as I mentioned, I'm going to actually now start from the beginning with the question, okay, what was our motivation to start this project after all? Well, we in our research group were interested in postural assessment. So basically measuring certain lengths and angles and ranges of motion of the human body, because being able to do that properly allows you to identify or diagnose potential deviations in a patient's posture, but also in the process of the rehabilitation of said deviations, evaluate if there is improvement or not in a more objective manner. And there are many ways that you can do postural assessment, and we're going to sort of rank them in a very simplistic way here in sort of this axis of cost / invasiveness / accuracy, because although they are different measures, they're somewhat tied. So in the leftmost part of the spectrum, you would have something like a goniometer, which is basically just a manual ruler that a professional needs to, well, use on the patient to extract measurements. Requires, of course, that the professional does it correctly. And on the other end of the spectrum, sort of like the ground truth, the golden truth, you have tomography, MRI, X-ray, which will give you then an exact measure of patients' postures or certain reference points that you want. And of course, this works perfectly, except that you are subjecting the patients to radiation, which is suboptimal, and there's a bit of a cost associated. And for particular things like ranges of motion, well, if you've ever been inside of an MRI machine, you know that there's not a whole lot of wiggle room in there to do range of motion. Right? Somewhere to the left of the spectrum, again, you have something like photogrammetry. So you take images, markers, you can extract information out of that, but that still requires you to, well, identify the markers, check the images. And in this spectrum, there was this one product we stumbled upon that for our group was particularly interesting, which is called the spinal mouse. And the spinal mouse is essentially a tool with which you can measure, using a wheel and some angular sensors, the spinal posture of a patient. And this aligned very well with our goals. So we looked at this product and we asked ourselves, in particular, at the features and at the price of the product, and we asked ourselves, okay, how can we improve? And so we came up with a little list of little targets we set in ways that we could improve on this existing project and come up with an idea that was somewhat better. And there were a few goals set here. So basically, we knew that we wanted to acquire both linear and angular positions. We set a few ranges and resolutions. And we had other non-functional requirements, like it being inexpensive, which is, of course, for a developing country like Brazil, where this was being developed, a big point. Be able to do cervical assessment and allow also for real-time visualization of the data being collected. And this is this goal setting is actually the first step in design methodology that we are following. So the PAL and BITES, the well-known design methodology, and you see in the corner there, this was essentially the first step in that, the informational phase. We moved on then to the next phase, the conceptual phase, where we were thinking, okay, we have these requirements. Let's think about what are the elements in a system that can actually solve that problem. And so we see here a very rough sort of conceptual signal flow of the product. On the leftmost, you have the patient and its spine. You would have, of course, some sort of measurement wheel, whose movement gets translated into some sort of digital information via an encoder. The angular measurement then happens with an inertial measurement unit, or an IMU, which is essentially an accelerometer and a gyroscope together. Those are crunched, these numbers are crunched by some sort of inexpensive microcontroller. We actually did use an Arduino in this project, and these then get transmitted to a computer that does the heavy lifting. So the next step is then, well, we identified the players, the signal flow. Let's put it all together in this embodiment phase. And the embodiment phase, as you see here, this was our very first prototype. We essentially just rammed everything together with a 3D printed shell, again, thinking about flexibility and cost effectiveness. You see there the microcontroller, the encoder attached to the measurement wheel, our IMU that does the angular measurement, and a little status LED and user button for the interaction. Okay, now we have a device physically, but our next step is, of course, to extract data out of it. We want to be able to measure the patient's posture. In this concrete case, it's spinal posture, right? So how do we do that? So essentially, we are talking about with the device, which I actually happen to have here, the camera. We want to measure a couple angles. We want to measure basically its pitch angle and a roll angle, so around this. And you see here, identify them with psi and theta, essentially. And then we, on the left image here, you see some frames of reference that we defined. Our main interest as a frame of reference is frame D, which is the point that touches the patient's back. And of course, we have a frame of reference, which is the IMUs, or the inertial measurement units frame of reference. And they're placed in such a way that translating the measurements of one to the other is trivial. So having that in mind, how did we proceed? We essentially, like I said, want to, in the first step, identify what are the pitch and roll angles of the device, standing upright, going down the patient's back. We start this by essentially taking estimates that use only our accelerometer as an input. So we basically do a little arctangent that just computes, okay, where is the gravitational pull? How is the gravitational pull oriented in relationship to the accelerometer's frame of reference? This is our first estimation. And the second estimation uses the gyroscope. And we're basically saying, right, the gyroscope gives us angular velocity. So we're essentially integrating this angular velocity to get angular position. And then we have our second estimate. We combine these two estimates then via a very simple method, which is called a complementary filter. And a complementary filter, as you see, is easy to implement, which is compliant or goes well with our little microcontroller we were using. And it essentially exploits the fact that our gyroscope has a high pass behavior, so it's actually a derivative of a signal, whereas our accelerometer is just like a low pass system. So in steady state, we'll converge to the measurement of the accelerometer, but the dynamic or the transients pull in the data from the gyroscope. So it works because the systems have those characteristics. Once we then have a sort of quality or decent pitch and roll angle estimation, the next question is, right, we are moving this guy vertically, so we're going down the patient's back. How do we actually reconstruct this trajectory? That is, if I am in a point P of K minus 1 in an instant, how do I find my next point P of K? And what we're doing here is essentially saying, right, here on the rightmost part of the equation, I essentially have a vector that starts off oriented vertically in the z direction. And this is the length of the displacement of the wheel. You see there the difference between the encoder pulses, d of k and d of k minus 1. A constant, which is essentially the radius of the wheel, and two rotational matrices for my pitch and roll. So we combine everything together and we can sort of stitch the little segments of the trajectory. Great. Now the question is, does it work, right? And to reply that, we constructed a little testing jig, which supposedly doesn't look necessarily like a human back, but it does contain the overall appearance of what this project or the product would be doing. And we then took our little prototype, attached a lot of optical markers to it, got an OptiTrack, which is a validated device with a known precision, and said, okay, let's see if the measurements actually match up. What we measure with the device and what the OptiTrack tells us. And those are the results. So you see, we have here just the graph for one run. We actually took 30 measurements in the paper. And you see in blue, you have the OptiTrack's trajectory, so what the OptiTrack saw. In red, the prototype, and in green on the side, the error. And you see that they actually follow along quite well. And you see here on the left, let me actually just drag the cameras from everybody. Right. The error that we accumulated for the two planes is on a sagittal plane, a linear error of 4.5 millimeters and 3.9 for the coronal plane. And the root mean square error was 27.5 on the one plane and 25 millimeters on the other. So considering how everything is fairly rudimentary, we were quite satisfied with the results there. So did we improve? So now let's go back to the beginning and ask ourselves, did we improve? For the first thing we were looking, so acquiring linear positioning, we achieved the 2 millimeter resolution we were talking about. And this you can see via the encoder resolution, wheel size, and whatnot. We did not, however, go over the 0 to 1.5 meters range. So this is open, but of course it looks very like it would actually do it. Acquiring angular position is covered. We do have this complete 0 to 360 capability with the 1 degree resolution. Inexpensive. The entire thing did cost under $100 to assemble. Cervical assessment is doable, would require, of course, a correct protocol to do so. So we sort of get a gray tick. And real-time visualization, as you guys saw in the video, is covered. So to close it off, what now? As you guys seen, we continue developing the product or project. It actually looks a bit different right now. It has a bit of a cleaner view. It is not 3D printed, but laser cut, which does give it a bit more robustness. The software is also improved, but there is, of course, a few other things that still need to be worked on, like the gray ticks in the previous slide, and other ideas that are always coming around. So that was a speed run, but I'm done, and I appreciate your attention. So if there are any questions, please.
Thank you very much, Martin, for this very nice presentation and for sticking at the time. The paper is now open for discussion. Is there any question from the audience?
Yeah, if I may, Juan Antonio Carretero here.
Please, Juan Antonio.
Yeah, just a quick question. What is limiting your range from 0 to, I think, 1200 or 1500 you were looking at? It seems to me as though you're using a potentiometer, aren't you?
Mm-hmm.
So is that what's limiting it?
No, so the 0 to 1.5 meters was, I think, sort of this arbitrary benchmark. Can we do this? Because if you're measuring a patient's back, it's unlikely that it's going to be more than 1.5 meters. So we just took it as a goal, sort of arbitrary, like I mentioned. But the angular, the displacement of the wheel is measured with an encoder. And the encoder has then no limitation. It can just rotate forever. And so there should be basically no issue in reaching the 1,500 millimeter range that we put in there. The only reason I gave it a gray tick is because if you really want to be tight about this, that's not covered in the paper. So I can't claim that it was tested. So.
Ah, okay, I see. So there is no limitation.
No.
So the way you showed it, it seems as though did the encoder actually look at the one you showed on the picture? Because that's
it actually did in that first prototype.
Okay.
I don't think you can see it in the picture, but we did use that Burns encoder that I showed there. In this particular picture, the image is taken directly from above, but it is indeed that little component there, that guy there in the middle.
No, it seemed to me it looked more like a potentiometer, not so much as an encoder.
Right, that guy is an encoder. And in this new version we developed, it's not an encoder anymore. It is actually a magnetic encoder, or it's still an encoder, but it's a magnet that rotates, and we have a magnetic field measurement in there.
And as I see your new prototype, the wheel is made, doesn't have the serrated figure. So you're not concerned of it not slipping. So I'm guessing that your patient is always has the back, a naked back, so that it would not slip.
This is a good question, and we ran a few tests with it, both on the naked back or also in clothing, and we never really saw slippage happening. I won't tell you that we have proper measurements of friction coefficients of stuff or stuff like that. We don't, but on a sort of like person by person basis, we didn't have any problems. But we were discussing at some point actually coating the wheel in a more rubbery sort of surface, because this was a concern that was raised.
You could make a groove and just put an O-ring.
Correct. That was an idea, but these parts are laser cut, so making a groove would probably require milling it, which then again is sort of like a cost constraint. So we didn't. And the thing that is somewhat useful in here is that you can look through it, so you have a better sort of view of what you're doing at the moment you're taking the measurement, which we also taught about.
All right, thank you.
Thanks.
Okay, time is a little bit tight, so maybe people willing to make further question can also use the chat for further question answer. So let's move on according to the schedule to the next presentation. The speaker is Osvaldo Rivera, and the paper is two-DOF robotic platform for balanced rehabilitation tasks. So Osvaldo, the floor is yours.